technical details just before starting this type of events. So this is the final workshop of the project FLOYD that will finish also at the end of this month, but a presentation about the project will be done. So we have some links to access more information on the project, website, LinkedIn, and then an email for anything that you may want to send in a written way. The program that we have prepared for you is this one, so we received it after registration. So I'm not going to detail it, just saying that this is a workshop about some of the most significant results of the project, but we decided also to invite some other projects to share also their results and at least to the project description for the ones that are starting, like Route 25. For the other ones, so some results will also be presented, so it is a joint workshop with a focus on FLOYD, but others will also have the opportunity to share the results, and that will be in session 2. So session 1 dedicated to FLOYD, session 2 with other projects, and then we have a joint round table or a joint discussion at 4:45. We also have invited two speakers, so Pedro Barradas from ITS Portugal, and then at the end Peter Stinkist from Carnegie Mellon University, and that's it. That also provide relevant information about V2X, ITS, so these vehicular networks or connected mobility as we called the workshop. So to give everybody a welcome, so I ask Paulo Firmeza, our director, to say some words and also to play a video about Altice Labs.
Okay, thank you, Francisco. Just very quick words. I know we are already late on the schedule, and I see a very dense agenda for today. It is an honor for us, Altice Labs, to host this final workshop of the FLOYD project here in our premises. And not taking any much time from you, I will give you just a small video just for you to understand what is Altice Labs, and then we will go on the program. Okay, so. in a nutshell, I will not take you any more time. So once again, welcome to Autis Labs. I hope you could have a good work afternoon, and I hope to see you soon. Congrats, okay?
Okay. So thank you, Paul. So I forgot to mention that the session is being recorded, as we said when sending you the Teams link for the session. Then we will make it available online on the YouTube channel of the project. For the questions that you may have for the presenters, please preferably put them on the Teams, for the ones that are remote, put them on the Teams chat channel, and then we'll present it to the speakers. Anyway, if you have some other question that you just remember just in time, please also use the audio to put them. Preferably put your questions on the chat. So as I said at the beginning, so these are the links for the project, website link, YouTube, where we have put some videos about the implementations we have done, some demonstrations. So we're not doing them live, but we have prepared videos with screenshots, etc., and some slides, mixed with some slides to describe what is going on in the implementations we've done and the demonstrations that we have done. So to continue, so I give now the floor to Pedro Barradas from ITS that will do the first keynote speech. Cala aí, onde é que está o link? Não está a funcionar. Está local? Não sei se é local. Qual é que é?
Good afternoon. Thank you so much for, first of all, the invitation, the kind invitation, and congratulations to the project. I have the role today. We presented in only a month ago in May in Lisbon during the ITS European Congress. And I thought it was worthwhile to reuse some of the slides, then reshaping a little bit the content to showcase you what is happening, what was happening a little bit in the past, where are we today, and how do we envision, or the European Commission envisions the future developments in the field of connected and automated mobility. So that's me. My name there, Pedro Barradas. I'm Chief Strategy Officer in Army's ITS, which is a company close by, located in the city of Porto. We develop software mainly for traffic management purposes and ITS services. And on top of that, Army's is also holding this year the presidency of ITS Portugal, which is a non-profit organization combining many of the Portuguese companies devoted to mobility, intelligent mobility. So in that capacity, I'm very honored with the invitation and very happy with the opportunity to present you a little bit what is happening in Europe around the topic of connected and automated mobility. So a little bit of background, and I'll try to keep it short because I know we're compressed a little bit in time. So, but just to give you a kind of background, this topic is not new. It was started to be discussed in the European Commission amongst many DGs there, bringing together not only the component of mobility and connectivity, but also the automotive industry. And the way the European Commission is looking at this is to achieve world leadership on the field of connectivity and intelligent mobility. And this is actually a race that is happening in between the three regions, the US, Europe, and Asia. I can tell you that at this point in time, we're just starting the race, so no one is winning, although you may see that there are very different approaches towards the topic, whether in Europe, where it's mainly bottom-up driven, with a lot of regulation in between to foster innovation and deployment. You see a much more innovative market in the US, where things are led by innovation and coming up to market, but then some risks are very high, and some big companies crash very often because of the uncertainty of what this new topic brings. And in Asia, you see a top-down approach, saying, okay, we'll do this this way, and we'll have it be finished by that date, sometimes failing to see standards, failing to see architectures, and then ending over finishing projects in a very short cycle that then needs to be restarted over and over again. So I would say that this is a very interesting topic to work in, but it's, as I said, just starting to be scratched. Back in 2007, when the Commission had the role to, under the mandate of the ITS directive, to regulate cooperative ITS, I was by then in charge of one of the topics under the CITS platform, phase 2, that you see there, and it's available online that you can check it later. I was chairing the working group dedicated to enhanced traffic management. So how to combine mobility, intelligent mobility, connectivity into more intelligent traffic management in our cities, in our road networks. And the discussions really came to the conclusion back then that there was a real serious gap in technical tools to promote appropriate interaction in between, let's simplify, the vehicle and the road, but there are many stakeholders involved, from OEM manufacturers, combining so many different applications inside the vehicle, to the road infrastructure and furniture equipment, using so many different types of standards and communications, to the road operators themselves, either cities or concession or national road operators, to the communication layer, of course, with so many different technologies to communicate in between these different individual systems. So obviously, and this is why I'm reinforcing, this is just being started to scratch the surface. Nevertheless, there was some insights. These automated vehicles will be computers on wheels. So there's a lot of software and code that needs to be developed so that they really understand the traffic regulations and the implications of that into safety and efficiency. So there's a lot of things going on in this field. And one of the needs that we identified back then was the need to deploy electronic traffic regulations. So to translate the UNEC code into software code, especially standardized formats that all the stakeholders can understand and interact with. Back then, this, and it still is one of my favorite slides from that period. This demonstrates the convergency between the cooperative element, the connectivity, and the automation in 3 layers. And as they move further away in time, and we are looking at 2045, 2050, they will become more and more interactive and much more merged with each other. The topic of enhanced traffic management comes under day 3. So very simply, day 1 is I know where I am and I know where I'm heading. So these are the basic data that I'm sending as a moving object. Day 2 is I start to share what I see. So beyond the line of sight, 1 kilometer away, I detect a roadwork site. I can communicate that with the cars behind me. Day 3, we share our intentions. So if I want to go left or if I want to turn right, then this type of interaction starts to be developed and shared. And day 4 is like the crown jewel where everything is automated and efficient and clean, and I think the utopic usual scenery around this. But we got this wrong. So when we said that day 3 cooperation starts, guess what? It doesn't start spontaneously. There's a really big difficulty in putting all of these stakeholders cooperating with each other, coming to the table and saying, how are we going to share our intentions? And is sharing intentions enough? Obviously it's not, so a new term to negotiate, maneuvers to negotiate intentions. And then we open up a lot of new opportunities for research and development, whether that's centralized or decentralized. There are so many different types of applications and architectures to be studied and developed. And of course, in the future, if we are going to decentralize architectures, nothing will be coordinated, it will be orchestrated. So a few examples here, just to keep you all awake, because you came from lunch, and I don't know if the coffee was strong enough for my speech, but things like vehicle platooning, speed harmonization, lane balancing, these were kind of the use cases that we were drafting back then. And these are not examples from the European Commission, these are from the US DOT. So there are trialogues ongoing constantly between the 3 regions, and because no one knows, no one has a crystal ball about the future, these 3 regions periodically every year meet together and discuss how to move forward, what kind of information and knowledge are they able to share, because this is going to be a global trend. Of course, everyone wants to get there first, but you want to get that right as well. So a few highway basic maneuvers, but for sharing intentions and negotiating maneuvers in the freeway. And you see that with these different geometries in road network, things complicate much quickly by weaving and merging and diverging into different lanes, into different interchange nodes. And then the complexity rises again when you come to the urban domain. You want to park, you want to depart, you want also to establish some lane balancing in the main arteries, and you have signalized intersections with different brands of traffic lights, different brands of vehicles, different suppliers of communication hardware using different standards. A very simple thing, which is a roundabout, becomes a really difficult challenge to overcome with cooperative and automated mobility. So based on this, there was work carried out with the 3 regions from then onwards, and those slides that were shared by the US DOT really gave us a hint, because also the US DOT came to the word negotiate, not sharing maneuvers, and this was a kind of a wow moment. We said, okay, how did we, without ever speaking to each other, chose the exact same word to describe what is happening in the, or what is going to happen in day 3. Guess what? Also, the European Commission didn't like that word. Negotiating was not in the jargon. It doesn't fit the taxonomy. So it took us a couple of years to get to the right wording, and what we have now is agreement seeking, which is much more policy correct. And in terms of mandating or orchestrating, we have prescriptive measures that will direct you engaging platooning or coming to an intersection, or waving or diverging or converging in a motorway. This is public, by the way, and I hope the presentation is going to be available for everyone, and I'm open for questions, so I'm more than happy. A few of the early cooperative traffic management use cases that we have identified back in 2017. Cross-brand cooperative lane changing. Why cross-brand and cooperative? This is really super important, because there are so many different vehicles, brand manufacturers. They really need to come to the table, discuss together what they are going to harmonize in terms of data flows, in terms of data categories for exchange, so that the safety and efficiency applications are worthwhile investing in. Again, lane merging, ramp metering, which is a little bit more exotic. I'm not going to waste a little bit time explaining that one, but on-street parking data, everyone knows what it is. And also traffic light data for promoting the use of public transport, emergency vehicles, prioritizing those at intersections, where some of the obvious use cases, low-hanging fruit that we have identified by then as the intersection crossing cooperative, by the way, in urban areas. Now, going back to where I think we wanted to end, the regulation, what is Europe doing and why is this relevant to this audience and today for these projects? Because there were some recommendations drafted in 2017 that are describing the need for pre-established digital traffic management plans. So one thing is to orchestrate traffic maneuvers. If you want to orchestrate, you need a kind of a score to play it, to play the music. Otherwise, it's really so nonsense and inefficiencies. So you need these digital traffic management plans and profile traffic management plans so that the vehicle, the infrastructure, the user can actually understand what that means and what's to expect in while moving freely in the networks. This led to this idea of making them available in the form of a digital library available through the national access points, which are single points of access that every member state has to build to provide access or to grant access to real-time traffic data, multimodal traffic data, travel information services, road safety related information. Everything needs to fall into that national access point to be reused, recycled, and it needs to be accurate, so the quality of the data needs to be up to standards and with high quality, otherwise the services won't roll. So to foster cooperation, I think we need something, as I described back in a month ago, we need to up the game. Upping the game needs to go from cooperation to co-opetition. We need the different brands to come together to the table and discuss ways to still compete, preserving their IP rights, but at the same time allowing some room for maneuvering for this convergence to connected, cooperative and automated mobility to be a reality. So in the framework of the revision, and I'm just really finishing just 2 slides, the directive that was published in 2010 was now revised and is being approved by the Parliament and the Council. This was done in the 11th this month, and it's mandating availability of crucial data in those national access points across Europe, real-time traffic data information, road safety related and multimodal travel information services. Also, the geographical scope now goes beyond the motorways, the 10T corridors. It's going everywhere into every single road in Europe. Also to mandate the deployment of essential services, mainly, and this is super important for today, CITS, so cooperative ITS, that needs to be also included in the impact assessment. But it will require new legislation. And the working program between 2022 and 2027, guess what, got the recommendations from 2017, and it's now up and running, so we will be getting some grants and opportunities under CEF or Horizon for promoting these recommendations from the CITS platform back in 2017 in the upcoming years. So all that related to the work carried out back in 2017, the Enhanced Traffic Management Working Group, which is, I have to say, pretty cool. So in October 2022, last year, the TRAN committee adopted the report on the adoption of these recommendations for the revision of the ITS directive. And as I said, it's going to cover all of the network. It's going to be mandated so the crucial and essential data to be made available in the network of the national access points, so that they are up to standards, interoperable and harmonized across Europe, so that you can go from Lisbon to Ljubljana and not worrying about a thing in your journey, except getting the right indications and do the trip safely and efficiently. And the communication infrastructure to be standardized into message formats to be used between connected and automated vehicles by the different stakeholders involved in the value chain of the service. And that's it. That's what I presented back then, and this is what I intended to present to you guys today. I hope it's useful information for everyone. Thank you for your attention.
So there are no questions from the remote audience.
Maybe they'll arrive later.
Thank you.
Okay, so just switching laptops. Okay, so continuing with the agenda. Okay, so technology not always helps. So now give the floor to João Silva, that is going to present the FLOYD project. So, João.
Thank you, Francisco. So good afternoon, everyone. My name is João Silva. I work in Capgemini Engineering and for FLOYD project, and I will show a bit an overview about the FLOYD project. So basically, in terms of agenda for this presentation, I will show entities that are involved in the project, the motivation and the objectives that the project, project structure, the use cases defined by each partner, the integration lines between the work developed by the partners, and also the last topic, dissemination and exploitation. So regarding the entities involved, so we have Capgemini Engineering, the project leader, Altis Labs. Thank you. Altis Labs, sister, research center, IT, Vortex Collab, and also with the support of Carnegie Mellon University. So moving on to the motivation that led to the project. So today or currently there is a big evolution in terms of autonomous features. And one of the main goals with that is to try to achieve autonomous driving concept. So this can bring several advantages. It can be the reduction of accidents resulting from human error, to be more accessible to a wide range of users, for fuel economy, improve fuel economy, and so on. There are some key drivers that can be used for this. So 5G networks, it's one of those. One of its subsets, which is ultra-reliable and low-latency communications, to be able to have very fast communications for autonomous driving, artificial intelligence as well, and at last, on autonomous driving applications to be able to assist the vehicle during its journey. So regarding the objectives, in a very generic way, the first main goal is to improve mobility services and to accelerate integration of autonomous driving in our society. And to do that, we are focused in a specific case, which is vehicular platooning. And to do that, we aim to build an end-to-end solution that can support autonomous platoons for the advanced use cases. So in terms of work package structure, so we have below the first work package, so which is for coordination and management. On the left side, in the first stage of the project structure, work package number 2, so it's more focused for the overall system architecture, the requirements, scenario thinking, the definition of the use cases of each partner. In the second phase, we have the more technical work packages. So work package 3 and 4, the third one, it's more focused for network management and enhancements. So for example, for management and orchestration for V2X, edge computing, the support between public and private domains. Work package 4, it targets vehicular connectivity and applications. so more between the communication between the members of the platoon, and also cooperative autonomous systems applications, for example. In work package 5, it's more for validation, demonstration, integration of all the solutions from the project. And in the last one, work package 6, it's more for dissemination, communication, and exploitation of the project. So in this diagram, it's a very, let's say, simple diagram with the use cases of the project. So we can see the public and private domain. In the bottom right part of the diagram, we can see the use case from Altis Labs, basically focused in the handover between public and non-public domains and 5G networks. Use case number 2 from Vortex regarding the safety and privacy of the communications between the platoon members. We have the use case number 3 from Sister regarding applications for the platoons, for example, for object detection. Use case number 4 from IT, which is focused in the offloading using Wi-Fi as well, and unlicensed spectrum. And use case number 5 from Capgemini on top, regarding platoon support using operation support systems to be able to adapt the network, dynamically adapt network, and improve also the performance of the network. So in this table, it's, let's say, a summary. It was in a later stage that were defined some integration lines between the partners and the individual work between the partners. So in the first integration line, it's regarding the public, non-public handover, where there was some joint work between partners. The second one, more regarding local cooperative awareness. So basically to have an increased awareness for vulnerable road users using, for example, roadside cameras and edge cloud computing as well. Integration line number 3, more for multipath and also offload data to using Wi-Fi. Integration line number 4, more in the metrics analytics and the use of NWR, for example, for metrics retrieving from the 5G core. And the last integration line, it's basically an extension of integration line number 2 with some add-ons regarding, for example, edge host application and multipath as well. So in this diagram, it's a very simple and high-level diagram with the architecture of the project. So we can see on the left side with the blue color, the public domain. On the right side with the orange color, the private domain. And explaining very briefly, so we can see on the bottom right the user equipment, which can be the platoon leader in this case of the platoon. It can be connected to 5G base station or Wi-Fi access point. It can be using some application for autonomous driving assistance in the edge cloud for latency purposes, the 5G core functionalities, and also management and orchestration components. So moving on to the next slide, there are a few numbers regarding dissemination and exploitation of the project. So regarding publications, so far it were made 24 publications in international conferences. There are several students working for the project, where there are 8 PhDs, 11 master degrees, and also 7 bachelor degrees. A logo, a poster, a brochure were designed for the project, and the advisory board is composed by Luís Simões and Visaveira. And that ends my presentation. Thank you very much, and now we can proceed to the technical presentations.
Okay, so we continue now with the more technical presentations. In fact, next one, it's me. Okay, so in one of the work packages, the work package 3, well, we have studied several topics. One of the topics of use case or applications of the 5G and the networks and help these V2X scenarios is edge computing. So, and then we thought that how could we address mobility and edge computing. So in this particular case, so there is a truck. I'm trying to point to, I think you can see it. Okay. So in this case, a truck is leaving a private network, in this case a PNI, so a public network integrated non-public network, so it's a slicing operator. So this truck leaves this entity, then crosses the public network, and then its objective is to reach a standalone NPN, so a 5G network instantiated totally in a private domain. So we have the public network with several runs or tracking area codes, simplified by different GNODEs, by different runs. Each run is connected to UPF, and each UPF is connected to an edge computing platform to run as closest as possible application services. And then we have on the top the 5G core and the central cloud of the operator. So this truck is moving, so goes from right to left, and when handovering from run to run, the idea is that it is served from the closest edge computing node. So these edge computing nodes are distributed along that path. So while moving, the trucks, or the vehicles in this case, is truck handovers. So since the handovers, at least to reach the closest one, if nothing is done, so the service is reachable through different IP, and in fact that's not so simple, because we also need, so if it was a normal network, a central UPF would be used, and without this feature of 5G, that is this service and session continuity mode 3, though this feature on 5G standalone, so allows anchor point of a session to change point of attachment. So it allows the PDU session established between the truck and a UPF, so when moving, to change that anchor point to another UPF. So it's a feature that was specified and designed implementation of 5G just to allow some mobility and this kind of edge computing. But that's not all, so something must be done. So the network must implement this feature, this service and session continuity mode 3, so that allows this session mobility inside the network. But with that, IPs changed. So it changed the IP address of the moving terminal, the user equipment that is now, in that case, in the truck, and also the services change IP if nothing is done. So, and then connections are established, etc. If the service is reached, so identified by its name, so different IPs represent different names. But the terminals are not always requesting a name resolution on the DNS, so it resolves the first time, then for a certain time it doesn't resolve again. So these will not work if nothing is done. So in a very simplified way, what we have done, so we have made changes in a set of components of the network. So, and we decided that this is the right approach. So we have a global name for the service. So the service has a global name that is known everywhere, that is converted in an IP address when this conversion is requested to convert the service name into an IP. So that DNS record is created in a central DNS. That IP that is returned, it doesn't exist on the network. So it is a virtual IP that is assigned nowhere, in no place. For the service to work also, so when deploying the service instances are deployed and started at each different edge computing node. So different IPs exist associated to the platform or to the application, but in every location the IP to reach the service is different. So what we have done, we have changed this UPF function to have NAT functions. So in fact what we do, so we convert the global IP that is never assigned to no entity. So in each UPF it is translated to the right IP that this application, that application instance has in each edge node. So with that, when the truck is moving, so the IP is seen, the service IP is seen from its location, always with the same IP. So when sending packets to that IP, so the packets are sent to a destination, and then in the UPF there are some rules that say that this IP should be translated into a locally served IP that corresponds to the IP service or that specific application instance running in the closest, and closest may mean many things, in this case geographically closed to the user equipment, to the truck location, and so it is served that way. So this minimizes, at the same time, minimizes the latency, distributes traffic, so the clients are always best served. So this is in a very generic way, the way we implemented it and the way we demonstrated it. For this, we have the tool that we used is Open5GS, so this open core, open source implementation. We also use the UPG travel ping, so it is a UPF implementation outside Open5GS. So it's one that is implemented in VPP. And we changed it, for instance, to improve that NAT functions that already existed but not operating in the way we wanted them to operate. Since we didn't have so many runs available, so here in Nautilus Labs we have a private 5G network, but with a single run, a single Gnode B. So we don't have enough Gnode Bs to test this in reality, so we use these UE run sims that many of you know to implement those different Gnode Bs connected to the core. And we used an open source implementation of an edge computing platform that is Edge Gallery, and we also had to modify it. So Edge Gallery, it's an open source tool. It is backed by many Chinese and Indian entities, also some Occidental entities are already working on it, like IT in Aveiro. So we knew about it, so we deployed it, and this has a common edge computing platform with a central node and an edge node. So from the central node you can upload workloads, and then through the graphical user interface of Edge Gallery, so we decide in which edges the workloads are deployed, and so you manage which workloads will operate in each edge node. So we used it with a central node, with 2 or 3 edge nodes, and we made that changes. So we corrected some issues with Open5GS code related to tracking area codes. So in fact, each Gnode B is a tracking area code. We modified Edge Gallery to integrate with 5G plane. It already integrates with it, but not the way we wanted it, to put there some different rules in the way we wanted it. So Edge Gallery has that advantage. It's different from the other edge platforms, edge computing platforms that you know, they don't integrate natively with 5G. Edge Gallery has that feature, so it has already the MP2 interface that ETSIMEC specified. It is implemented by Edge Gallery, so that was also one of the arguments for us to check this. So it has these native integrations, but not operating as we wanted, so we changed it. We added or changed the way the central DNS works in Edge Gallery, so to return that global IP, we modified the travel ping UPG, the UPF, to receive those traffic rules. And then to demonstrate it, we also developed a video streaming server application to be used and to demonstrate the feature. So in our case, so the truck is moving or simulate is movement, and then it is receiving a video stream that changes. The content is different in a transparent way when it moves from point of attachment to another point of attachment. Well, to have more details, so in the YouTube channel we have uploaded a demo, a video regarding this demo, where in a very detailed way this is explained. So if you have any question, please put it in the chat, and then at the end in the question and answer slot, we will answer them. So thank you very much. And now João Pedro Fonseca from Capgemini will also do another presentation.
Hello, good afternoon, everyone. We at Capgemini try to focus more on the use of mobile edge computing in a private scenario, and we have done some work with our partner Sister towards that end. So we focus more on the platoon scenario, and where we have a platoon leader, which has a camera and is streaming some video, or can stream some video to the network. And the idea is to allow the platoon to stop when some object is detected on the road. And we thought about it, and we know that this kind of processing requires some computing power, and also some energy, and it's not feasible to be done in a truck, or at least it will take some. After some time, this will stop working. So we thought about moving this or offloading this service to the edge, and the idea was to create a near edge object detection service. For that, we have focused on the use of open source solutions for object detection. We used YOLO in this case. We also thought about how we could do the displacement of the video, taking into account that this streaming should be very shouldn't have a lot of latency, because we are talking about traffic, and we don't want we don't want latency when trying to avoid an accident. And for that, we are thinking about the use of 5G. So for the communication of the video, so this would be the medium that would allow the sending of the video to the near edge site, where it would be then processed. And after this processing, when an object is detected, we would then advert the vehicle or the platoon leader that an object was found, and that the emergency braking system should be actioned. So for that, we thought about the scenario in a real world. So the colleagues from CISA already have a platoon that could do autonomous driving, and we have been working on trying to create our own solution for 5G private networking, and we have made use of custom off-the-shelf hardware to build our G-Node B solution, as well as the radio. We used an USRP, so this is similar to an SDR, and we have used OAI, or Open Air Interface, for creating a G-Node B that would provide 5G or private 5G network that would be accessible to the platoon leader, which would then stream out this video to the network. Concerning the core of the private network, we used the solution by Capgemini called VINGC, and for the near edge MEC solution, we used the EAAP. So this is an mobile edge computing solution by Capgemini that also allows for the placement of different kind of containers and edge computing solutions on different locations. We have integrated this scenario, and we have a demo where this platoon leader receives this warning message when an object detected is an object is detected on the road, and we have it available on the YouTube of the video of the project. And concerning this demo, with the tools that we have used were mainly the ones that I've described before. We also have made some changes to YOLO to create this warning system that would allow the platoon leader to stop its movement. And we also have made changes to alternative edge computing platforms, or open source ones, namely the Intel Smart Edge and I'm missing the name of Edge Gallery, and that's all for now, I think.
Okay,
Yes, thank you very much, João. So please, there are still, I think, no questions on the chat, but please don't be shy and put questions. Also for the audience or through audio, you can also put the questions, even if you prefer if you put them on the chat. So continuing now with the second topic, network measurements and prediction, also one of the topics that the project addressed. I'll give the floor to Professor Ana Aguiar, that will now do this explanation or presentation.
Okay, thank you,
Não
Francis.
sei se queres usar um ou outro.
I don't know, whatever. I'll probably stay here.
Okay, if you
yeah.
talk to the microphones, there is no need for that.
Yes. So I'll also try.
We are 15 minutes delayed, so not that much.
I hope I'll not increase that by now. So we'll start with our use case. I mean, we had, as we mentioned before, about a vulnerable road user crossing a street somewhere, being observed by a camera, and somehow through a pipeline of services that can be located in any computational node, sending a warning at some point to a vehicle, or letting him know in advance of what he can detect himself. So we have another, that's the application layer, right? So we are going to talk below this we have a computation layer with multiple nodes where you can distribute the computation. And below that, interconnecting the nodes, we have many different wireless technologies. Well, some wired technologies too. And that's what we will be working on. And now, precisely in this first part, I'll be talking about these Wi-Fi links that exist to a large extent in our cities, but they exist in the cities, but they are currently not used for mobile nodes. But they could be, some of them have very high throughput, and they could support cellular networks when there is low connectivity or the cellular networks are crowded. So we were measuring this. This was part of WP4. We developed YPerf. It's a tool to do two things. One hand, collect data, and also for testing decision-making in real time. So this has two functionalities. On the left, we have the mobile client. On the right, we have the access point. First, to collect data. In this case, we are sending data very heavily, making the channel busy. We are collecting data on the receiver side, as calculating throughput, is just counting, annotating it with GPS, and then sending the feedback and collecting the data in this network performance database that you see here on the left. It's not highlighted. Then we have the second function, which is decision-making testing for network management. This is what you actually would do in real time. And in the real time, you will not be sending data at high, just for measuring the channel. So we have a channel monitor running, measuring both the data rates and several parameters that are being on the wireless channel. This data is being collected also on the same network performance database. So we have historic data and real or very short time data. And then, oh, sorry, this is in Portuguese. I didn't notice. Anyway, then we have the decision maker. We can actually then, from the collected data, do some estimation, prediction of what's going to happen, and then make the decision. So this is all, this blue part runs in real time, and what we are going to talk about next is about this throughput estimation, okay? So now, first of all, with the red part of the previous tool, we collected two independent data sets in two totally different situations. One was in Gaia, the other was close to FEOP. One we were used for training a model, and the other was used to test the model. The devices were the same. Then we use a very specific kind of model. It's symbolic regression. The advantage of this model, it is interpretable, and it is simple to implement on restricted devices because it's much smaller and much easier to compute than the classical, well, everything we know as machine learning. But this is trained in a slightly different manner. It's a meta-heuristic with genetic algorithms, which gives you a lot of solutions. It's just solution space exploration. And we choose the one that you see there in red. It is the one with the low expression, the low complexity of the expression, and actually a quite high, a low estimation error, so a high quality of the regression. So just briefly the results. This is the symbolic red line and yellow line. These are the things we developed. And you can see to the left is better. So this is a cumulative distribution function. To the left is better than to the right. On the x-axis, you have the estimation errors. And you see, we are actually always the best or the second best for 802.11n and 802.11ac. Throughputs for AC are already on the hundreds of megabit per second. So this is competitive with cellular networks nowadays. And this was a moving vehicle. Okay, for 802.11ad, which is the millimeter wave Wi-Fi, the performance, well, we're still among the best, but the performance is very bad in general, so you cannot really use this kind of approaches there. But this symbolic regression with the unscented Kalman filter has actually a very good performance for real-time network management for a moving vehicle. For attaching to Wi-Fi. We have another work on this, which is done by Moshe. He's working on reinforcement learning to do a better decision on when to change access points, and that will be on the YouTube channel also for you to see. Just for millimeter wave, what we tried there was to try to not predict anything, but just try to do a position-based selection of the sectors. I hope that next week, I asked Danielle to do a video about this, so next week we'll have a video about this work also on the YouTube channel. So now, this would be the topic on the physical layer. Now I'll be moving to something we did with Altis Labs, which is going back to our architecture there. We have these nodes on moving nodes, and we have the services somewhere in the edge. We've all been talking about this. And although the networks nowadays are not optimized for low latency, we still would like to know what kind of latencies can they provide. And what we did here is to perform active measurements again with a 5G client. Connecting to a 5G is a non-standalone, so it is a commercial network, and connecting then to a server running in a home device in the same city, just using also the commercial network for the wired access. So this is a over-the-top service, right? Not hosted at the mobile. What we did after measurements with a series of packet sizes and a series of interpacket times, I'm not going to go into those details, we just varied these so that we could then, when we observe something, sort of disambiguate if it's caused by the packet size or by the data rate or by the interpacket time. So like this, we have a series of parameters that allow us to sort of not stop at hypotheses that we cannot, reject afterwards. So we also took some care not to overload the channel. Before that, so how are we doing the measurements? One very important thing here is the synchronization among the two nodes. Because we are doing one-way measurements, we are not doing back and forth and dividing by two, because for the kind of latencies we are talking about, tens of milliseconds, that is no longer the assumption that you have similar delays in both directions is no longer really valid. So we are measuring using LipPCAP at the network layer, and of course synchronization becomes a problem because we have to synchronize the two nodes. We try to do this using GPS. It doesn't work very well, even when the GPS is right outside the window, because the GPS, the poor GPS connectivity is giving you bad timings, so we had to throw away those data sets. We synchronize it with NTP. What you can see here, on the left you have NTP synchronization over 5G, on the right over wire, and it's at 1 order of magnitude, the synchronization error between the two. Okay, so NTP over 5G, because of the variations, probably on the wireless channels, whatever, we have still, both are sub-millisecond, okay, so we can synchronize less than 1 millisecond, but they are still, it's much higher if you use 5G plus wire than if you use 2.5G. So these are the data sets we generated and shared with both Capgemini and Altis for some work that is coming up front. And I'm going to talk now, me and Andre, is going to talk about this dataset V2. So first of all, our measurements have no impact on the network traffic. You can see there's a very low rate of outliers of on the measurements, and the packet losses are less than 0.0 something most of the time, actually. So second thing, we discovered this, which is an abnormal pattern. We would expect the delay to be a random, and this is not random at all. So we developed a method to detect this automatically, and we can detect that it happens mostly, or we observe this during nighttime. So these are periods of very low average delay. So we think that this happens all the time, but we only observe it when it is not masked by much higher delays caused by something else. So we looked into this to try to find out what this is happening, why this is happening. The reason we look deeper into this is that when we are talking about low latency, if there's something creating a non-random latency, we may want to find out which element it is to deal with it. So it's a sawtooth pattern. We use a range and a period to characterize it. Two things. First, the range is always, remember we have a sub-millisecond precision, so this is 5 milliseconds of range. Then the range does not vary with packet size, interpacket time, or time of day of the measurements. This is what these images show. Then two other things. The period, so the length of this sawtooth, does not vary with packet size, but it increases linearly with the interpacket time. So now we are still looking into this. We have been able, so it looks that it's caused by some TDMA mechanism along the way. We know it's not caused by the 5G device we used. We know it's not caused by the GPON downlink. We are now exploring where it is the 5G. There is something on the 5G scheduling on the non-standalone or on the TDD or on whatever mechanism it is that may be causing this, because this may have an impact on standalone or not. We don't know as long as we do not find out. So with this, I would hand over to Andre. To show what they were doing on prediction of this measurements.
Okay, so let's turn for, as I was saying, for Andre to share what we have done. So Andre, whenever you want, you can. Okay, so Andre is participating remotely. So he'll do it from his place.
So I will start. Okay, so hello everyone. I'm going to talk about our work on measurements and predictions. As I already said, we choose the network latency as an important KPI for edge applications. So the analysis made was the prediction of latency for future times. First, we use the Prophet. Prophet is a time series library from Facebook. It's very user-friendly with automated process to simplify the forecasting time series. So we don't need experience in data analysis to use it. With this library, we performed some tests trying to improve the results, like grouping the data with different group times. We try to filter by different packet size, and we try different group functions by average and by percentile 95. We observed the results of the Prophet. At the end, the best configuration was grouping the data by 15 minutes using the percentile 95 and with all packet sizes. In picture, we can see the forecast results, where is visible pattern in data, and this pattern can be checked in Prophet components, where we can see the data train and a daily pattern, where we see the less delay during the night and more delay during the day. That is an expected pattern for a network. Okay, then we use the recurrent neural networks for forecasting. There are network architectures developed for processing sequential and temporal data using cells with internal memory. What I mean, these cells can select the information is helpful or not to predict the future of the sequence. In this work was used the LSTM cells type. So for we have the better result, we can define some parameters that is called hyperparameters. And in this project, we tested different learning rates, optimization algorithms, loss functions, activation functions, and the different number of nodes and layers in network. Now we can see the best result we have. We can see a confidence interval that we made using the average error when we trained the model, adding and subtracting the average error to the forecast value. As a result, we had a very good forecast of the trend. And if we identify the height moments in the maximum forecast, maybe it will be possible to manage the network, preventing the network degradation, for example, for platinum service. At the end, we developed the API to show how these predictions can be used for external applications that can returns the values or the graphic of the predictions based on location and the predictions time range that we need. This kind of API is already being targeted by the GSMA for exposing network data and related function features. The GSMA is a global application unifying the mobile ecosystems to help the business and the society. And I finish there, so thank you.
From our audience online, we have a question from José Carvalho to Professor Ana. He's asking, you present absolute errors, but can you show it in error rate mode, like instance BER?
No, we only measure this as a throughput prediction. However, since the data was collected while filling the channel with data, I mean, we were really blasting data through the channel. All the throughput that you see on the we could probably do it. We did not collect the BER, but I would say that all the errors in throughput that we are getting are going to be caused in reality by wrong estimation of the BER. We have another paper also done in FLOYD, which does this for rate estimation, so MCS, and in that case, that will lead to higher bit error rates, but not in these results.
Okay, thank you, Professor Ana.
Okay, any other questions from the local audience or from remote people connected to Teams? If you want to switch on your audio and put the question in real time? No? Okay, so if not...
There's another question
from
the audience. For Professor Ana, again. We observed, it's from João Almeida online. We observed the same sawtooth pattern in 5G Mobix project in the NOS network, but didn't explore the causes. So this is just a comment.
This is wonderful. Who's the name? Because one question we had was, we are debugging this, right? So whether it is only the Mail network or we observe it in other networks, we have not yet. I think we did a very short test on a Vodafone network, and we also observed this. So if you have it also on the NOS network, we should get together and try to figure out what this is. But that's great, thank you.
Okay, thank you.
Okay, another chance for questions.
Yes, Ponce, I have one for you. You were referring, can you hear me?
Yes, yes, you can hear.
You were referring about virtual IP that is generated, but how can you guarantee that IP is not used elsewhere in the network?
It must be a public IP, so it must be an IP assigned to the operator,
Okay.
but it uses that public IP, but doesn't assign it to in any device.
So you have a pool of IPs that you use for that?
Yes, you take a small part of your IP addressing space and use a /20. Well, it depends on the needs, but a /28, /27 from your public assigned IP addresses, v4 or v6, and then use it for this.
Thank you.
Okay, so since you are a bit delayed, so we move on to the next session, but still, if you want later to put questions to the previous ones, please feel free to do so. So the next session C, it's about 5G monitoring and control. It is going to be made by 2 sub-presentations, and I'll give the floor to João Silva from Capgemini.
Okay, thank you, Francisco. So just to give a very brief overview regarding this topic, so I will divide into different topics. So for the RAN monitoring data, and also regarding the retrieving of 5G core metrics, analysis, and also prediction. So to do this, this is basically the setup that we've built. So we have on the left, it's the complete the setup for this, but I will focus first in the RAN monitoring data part. So we've used for user equipment physical hardware, we tested 5G module for this, SIMCOM, and also an USRP B210. We've integrated these with the RAN part. We used as well an USRP B210 and some open source software for these, which is OpenAir Interface and SRS RAN. So there was the need to integrate with a radio intelligent controller. We've tested multiple possibilities, such as FlexRig, MicroONOS, or RANRig as well. But the one that we managed to integrate successfully with the orchestrator and with the RAN part, it was FlexRig, which is also from the OpenAir Interface Alliance. And on top, we have the management and orchestration component, which in this case, we've used also an open source solution, which is OwnUp. So in these slides, it's a very brief workflow regarding this part. So on top, we have the orchestrator, where it's possible to define update policies. It can be, for example, to create a new slice, to delete a slice, to adapt the computational resources, for example, regarding the RAN. We've integrated these with the RIC, the FlexRig in this case. There was no native connectivity within both, so we had to create a A1 adapter, which is basically a REST API to allow the connectivity, A1 in connectivity between orchestrator and RIC. Regarding FlexRig, we associated with an XApp to monitor some metrics regarding RAN, and then to make the connectivity, the E2 connectivity to the RAN to be able to collect some statistics. And so the FlexRig or OwnUp could react or act in case it's needed. Moving on to the 5G core part. So basically the setup, so we've used the user equipment and the RAN integrated with the 5G core solution. In this case, Capgemini's VI NGC that João mentioned before. So with all the control plane and user plane functionalities. After that, we integrated with an external NWDAF to be able to collect 5G core metrics. And with that, we've integrated with an intelligent artificial intelligence platform, which is Capgemini's Net Anticipate, to use that data and to try to make some predictions to improve the network performance. So in this slide, it's a very brief overview regarding this work. So we've made two types of predictions. One of those was regarding network function loads of the network elements from the 5G core, for example, AMF, SMF, UPF. And the other type of prediction, which is in this slide, it's regarding network slice instance loads. We can see on top an example of the metrics that we've collected of the data set. It has information, for example, regarding the slice type, number of user equipment, PDU sessions, also CPU, memory, disk usage, and also network function load average. With this information, we were able to use Net Anticipate to apply some models to try to predict network slice instance loads. In this example, it's a machine learning algorithm for regression, XGBoost in this case. In the bottom left, it's possible to see some possible graphic visualization with Net Anticipate regarding the model that we've used to compare to other models as well. And in the bottom right, also a possible graphical representation, in this case to show the influence of the variables from the data set to try to do this prediction. So this is a very brief overview regarding these two topics. We have a demo video, which will be available in the coffee break with more details regarding this. And also in our website will be available as well some more technical details regarding these two topics. So, and that's it. Thank you.
Okay, so
So I'll be telling about closing the loop, because all this data, all this analysis is very good for some human to analyze, but it's good and it's important, especially to close some kind of control loop within the network. And vehicle networks are a very, very special place to show this, because these networks are a good example of how dynamic networks can be. And we can't have people controlling them. So we need to collect data, we need to analyze it, and we need to take decisions and then enforce them to the network and close this kind of control for optimizing, really, for organizing the network. 5G provides some means and some standards for doing this from the beginning. One important element or system or set of systems is the NWDAF, the Network Data Analytics function. It is a number of functions that is in charge of taking up all measurements, all information, collecting it, and then doing the analytics that can be done according to use cases. You can take data from other network functions. You can take data from the user plane, from the control plane, from the OAM, and even from the external environment. And then that analytics will end up as notifications, as analysis reports that are delivered to the network functions, and those network functions on the 5G core will make decisions based on those notifications, on those analysis. We have done an example of this. This is a very wide area, because you can have a lot of use cases. We have implemented a very simple use case, which I'll show you. So we instantiated basically a network. We have an UPF, which we instantiate with the travel ping, a 5G core with Open 5GS, and then the OAM we implemented it using TIG stack. We instrumented somehow UPF to generate IPX records for the traffic that it is delivering. So these records will be delivered to the OAM, in this case to Telegraph. Telegraph will produce aggregated data that is delivered to the NWDAF. The NWDAF then, in this case, implements a very simple use case. This use case is just, well, we are assuming that that little car there is traveling around, and then some kind of priority platoon, for instance, arrives and has some special needs, and then we can very surgically take decisions and notify the PCF, and the PCF is the policy control function, so it's in charge of policies for the whole network, and I mean policies user by user, service by service, not general network policies. And then the PCF will set up a rule on the session management function, and this the session management function will enforce that rule over the sessions that are already on the network. So we are doing this session by session, user by user, and this actually closes the loop. We detected in this simple use case, we detected the platoon entering the area, generated a notification, and somehow changed the behavior of the network with who was already there. You can watch this in detail, this demo in detail, in video and on the YouTube channel of FLOYD. And that's it. Thank you.
Okay, so you, Kale. So we move on to the next presenter. It is Pedro Santos from Sister and ISEP. Ok, so. Mas as pessoas não vêm.
Well, hello, good afternoon everyone. My name is Pedro Santos. I'm from Sister ISEP at Porto. I'll be talking about this in this final talk about V2X applications, connectivity, and platooning. And I'll start with the first topic. There will be three topics in this talk: 5G enabled connected platooning, also which will be presented by me; security for platooning, presented by Fernando Alves from Vortex; and also finally work on multipath, presented by Professor Ana Aguiar. So, starting with the first topic, 5G enabled connected platooning, I'll be talking about three things here. I'll be talking about radio models and physical MAC solutions for vehicular communication. I'll be talking about simulation of cooperative platooning using the ITS stack. And finally, I'll be talking about a 5G enabled emergency braking application that also has a demo associated. So, starting with the first topic, and this is work mainly carried out by our colleague from also ISEP, Sister ISEP, Ramiro Robles, also with some other students. So we've been working on multiple input, multiple output line of sight channels, or communication systems, more correctly. Also with considering round reflections, as we see on this image over here, where we are considering the possible reflections of the wireless signal on the floor when we have a communication between two vehicles of a platoon, right? So we also have analysis of V2V channel statistics when there's double scatterer interaction, also a new geometry-based stochastic channel for the Manhattan grid. moving forward, we have also on this topic an analysis of interplatoon communications for the emergency brake collision calculation. Authentication and security at the between the communications of the platoon through a physical layer using the special signature of the platoon, and also we are performing using AI to perform channel prediction using AI again. So this is work done also using some real data that we through interactions with partners. A final point is also the implementation of the successive interference cancellation non-orthogonal medium access with retransmission diversity, also which I believe is being also implemented by some partners. Also, a lot of this work gains from synergies with another work, which is with another project, which is Insect, also of which also Sister is a part of. So moving forward to the second topic, I will talk about the work that has been also ongoing at Sister for some time, which is cooperative platooning. So in this case, we ask the question, can we use these cooperative awareness messages, which are essentially messages defined by the ETSI ITS standards, which essentially are about each car sending periodically, let's say every 10 times a second, their position, speed, and direction. And by having all cars sharing this information, again, at 10 Hertz frequency, other cars can be aware of what's around them and can have an idea and plan for avoiding, for example, collisions or for cooperative maneuvers. So, but in fact, the standards actually say that the rate at which we transmit these messages, these CAM messages, can vary with respect to some kinematic thresholds. So if I'm steering too fast, if I'm accelerating too fast, the frequency of these messages can actually increase or decrease. And our colleague Enio Filho was curious, okay, if we change the values of these thresholds at which we should send messages, let's ask two questions. So does the platoon still operate correctly without any flaw? And are we creating too much noise in the network by just sending a bunch of messages that are unnecessary? So it turns out this is not a very, does not have a straight forward answer. There's a sweet spot in between the number of messages that we send and observing that the platoon is performing correctly, both in terms of the distance error of the vehicles between themselves, so the error between the intended distance and the actual distance that we are observing, and the error between the angle, the steering angle that we want and the one that we are observing. So all of this comes into play in terms of having a platoon that is purely, in which each follower is purely listening to the CAM messages of the car in front and reacting to those. So no, let's say, proactive communication between them, just receiving the CAMs and actuating in response to that. And so by varying the thresholds, the kinematic threshold values at which we are going to send the messages, again, we find that there's a particular profile where we are sending not either too much nor too little messages, and we are still striking a good balance in terms of the performance of the platoon. So, and there will be more details on a journal paper that we had on this. A final topic on this is the 5G enabled emergency braking. Essentially, we have a platoon that is approaching an area where there's a pedestrian. However, the vehicles cannot see the vulnerable road user. However, we have some communication infrastructure, either 5G or 802.11p, a local edge network, and a camera that is able to observe the pedestrian. So what happens now is that the object node detecting, the edge node performing object detection will detect that there's a pedestrian ahead, and this message will be using the video stream from the camera, and in the second step of the scenario, we will have a message being sent to the vehicles so that they brake in time and no collision happens, right? So we had the first implementation of this same scenario with 802.11p. So we had a camera, an edge node, and a roadside unit in a small test bed. So we can see that we actually implemented this in our laboratory where we have the roadside system. a makeshift obstacle, and then our scale vehicle, which is a robotic remote controlled car, but in this case it's navigating autonomously using camera and LiDAR, and it's also equipped with an 802.11 onboard unit. And so we were interested in measuring the end-to-end delays, since the camera observes the pedestrian until a brake command reaches the vehicle actuator. So going from the roadside infrastructure until reaching the vehicle and actually telling the vehicle to stop. And so we observed that in this very controlled scenario, we were getting values between 45 milliseconds and 72 milliseconds. Of course, these are highly optimistic. We did try to induce some interference, although we were not very successful at that. So this is really something definitely that we will revisit. Yeah, and so this definitely tells you that there's not a fixed value. Actually, it will be a distribution. This latency will follow some distribution that we need to further clarify. And the final slide that I have, which is the evolution of this, is when we have not one car but two cars, and now the information is being sent not via a local roadside unit, 802.11p roadside unit, but actually from the 5G network. And in this case, we see the front vehicle. Both vehicles are equipped with onboard units, and the front vehicle actually also has a 5G network. And so we are replicating the same scenario, but instead of using a local roadside unit, we are actually using the commercial 5G network. And that's it for my side. Check out our demo in the next session demo. And now I'm going to turn over to Fernando Alves. Thank you so much.
Yes, okay. Thank you, Pedro. Yes, as Pedro said, so the videos are already available on YouTube channel, so you don't have to wait for the break, but you do it and keep your focus on the presentations. So now I'll give the floor to Fernando Alves from Vortex.
Thank you. So at Vortex we were focused on the security part for the platoons and for the V2X communications. And so we developed two main contributions. The first one is the privacy for the platoons. So we have two main issues here. The first one is that when a truck is joining a platoon, it may want to have its identity preserved from the platoon elements. And the second part is that a platoon will want to have its communications protected from outside observers. So, for example, if you look at the picture, you have a platoon in there and you want the communications between the trucks to be protected against the other cars that are passing around it or infrastructure and so on. So for these two objectives, we developed a solution that comprises a public key infrastructure, okay, so that the trucks can authenticate with a central authority that will say that the truck can or not join a platoon. And once this is done, the existing platoon will receive a confirmation from the central authority that, okay, this identity can join. But this identity is also hidden, so that the trucks know that whoever is joining is allowed, but they don't know who it is. And hence we get the first part of the privacy. The second part, we have a key rotation system where the platoons obtain the same symmetric key for efficiency, and they always communicate using this symmetric key that will be used to encrypt and authenticate the messages that are exchanged within the platoon. When elements join or leave, this key has to be rotated in order to leaving elements to no longer have access to the messages that are being exchanged. The second part, or second contribution actually, is related to what Pedro was presenting. So, in these V2X scenarios, there are a lot of cases where you have very low latency requirements. So, for example, for the emergency braking, you have like 80, 100 milliseconds between sending a message and actuating based on that message. And we also wanted to include authentication here because you don't want rogue elements to send messages, for example, warning messages that the car should brake in situations where it shouldn't. For example, to steal the values of whatever is being transported or wherever you can imagine. So we needed to develop a solution where an entity can authenticate another entity within those 80 milliseconds and without requiring a third party to make this connection. So this is basically the regular PKI. We wanted to avoid that. So this is something that we're developing right now. This is a solution that whenever a vehicle receives a message that comes from another vehicle, it includes a signature that can be validated without requiring a third party and without requiring any further connectivity. So if the car, even if the car is only receiving local messages, it can still authenticate the sender. This is based on attributes-based encryption and on multi-party computation. It's still focused on also in efficiency because of the message sizes and the transmission times. And also this authentication mechanism does not require revocation lists. So this is our contribution. Now to Anna.
Okay. Thank you, Fernando. Okay, so Anna will present again.
Okay, so this is, I told you before already that Wi-Fi is widely available on urban areas. That's what that picture on the left shows. Well, your right shows that you can see that's the availability of Wi-Fi access points on roads in the city of Porto. And you see that most of it is way above 10 available access points in each 20 by 20 not centimeters, meter cells. So Wi-Fi is there, and we should be able to use it, but it's not easy, and everybody knows it's not easy to connect to Wi-Fi and then to roam around using Wi-Fi access points. So the idea here is how could we use this access point to take away from the car sensor data, sensor stream data. This could be videos, this could be LiDAR, but this could also be smaller data, just taking it off using Wi-Fi. And the idea here is that multipath transport. So not trying to do this at the lowest layer, but trying to use the transport layer, trying to connect to more than one network and use this multiple connectivity to then send more over the ones that have a better connection and send less, or then shift traffic around according to the quality of the connections. And so that's what multipath is for. So this was one of our proposals. We are still evaluating it. So the idea is that we have an application on top. Those squares are the frames that you would have for a video, or the point clouds for a LiDAR. Underneath you have this multi-access RTP, which is built on top of the RTP, the real-time protocol. It's a very old protocol designed for multimedia transmission, runs on top of UDP, and above all, it does not have any kind of reliability. So it does not delay or retransmit by itself. The key part of this protocol is then how do you shift the data among the multiple connections that you have. Okay, so that is the scheduler. As we already had seen for Wi-Fi, we are going to rely on a context-aware scheduler. This means it's using your current your current position, the speed, the heading, eventually to choose which other kinds of data it's going to use to decide where to send packets to. And of course, we are using here the network performance monitor. You remember the database that I showed in the previous presentation? It's the same. So you can be collecting this all the time and then uploading it to a centralized base station so they can keep track, not the base station, a network performance monitor station that in the 5G networks is somewhere on the NWDAF or somewhere there. We are not concerned here about how the exact implementation of this station is, but we do have, it's a geo-reference station, and it contains data like round-trip times, number of bits, the jitter. It can also contain throughput data, bit error rate, so it can contain different types of data collected by different types of devices, geo-reference. So for each position that you are in, you have a set of data measurements from previous times in your surroundings, and you can use that to make your decision. So the key thing, or one of the main reasons why we decided to use the RTP is that you also have RTCP, and the real-time transport, the real-time control protocol. It's automatically, well, it by default collects measurements about the quality of your session. So also at the application layer. And with this metrics would be additional data that we can then also input in our network performance manager. So not only lower layer metrics like we were talking about before, but also this high session layer metrics. So this is the was also sort of built. And then we have our experimental setup, which comes again from the vulnerable road user use case. We have a camera. It's sending data via, well, some device. And then we have our multipath gateway on a Raspberry Pi. The reason we have this on a Raspberry Pi is that then we can implement different types of multipath schedulers, multipath protocols. Ours is not the only one. So we did implement ours. This is a very complex picture, but just in blue there, does this have a cursor? So here in blue you have the data plane, and we would have our context data coming from outside in this orange, and our positioning coming from the GPS. And then we have our scheduler, which is the smart part of this multipath gateway. On the other side, we have a virtualized edge infrastructure. Of course, we need an endpoint for the multipath transport. Always need. You are building a multipath tunnel in any way, and you need a multipath receiver, and then you connect to the receiving service. We also implemented in another task an use the OpenMTP MPTCP router. There it has an implementation also for the Raspberry Pi, so that it serves as a baseline for our comparison. And this is our setup. I will not be able to show you any results because we have not finished processing that, but I'm going to let Bernardo explain what he did. Before that, this is our experimental setup. Oh, well, I cannot. The cursor doesn't work. So we are doing this in the School of Engineering. We have an access point. We have a 5G base station that is, well, somewhere there. And then all the node.
And we are using several different schedulers, some more traditional and some more complex. And in the end, we compare them and see which one is best.
Yes, exactly. So now I'll let Bernardo, he's here, explain to you what he did.
For this part, we are using MARTP to send a video in MPEG format. And we are using several different schedulers, some more traditional and some more complex. And in the end, we compare them and see which one is best.
I thought that this was a very short explanation. I would not do it shorter. So, and it is his work. So, as I said, we will put the results also next week on the once we have decent pictures. We'll put them on the YouTube channel. Okay, thank you.
We have a question from the audience, from online. José Carvalho is asking to Pedro Santos, what is the velocity of the vehicle? José Carvalho thinks it is important to reference the 50 milliseconds to the velocity of the vehicle.
Right. Well, the velocity, I am not fully sure. It should be under 20 kilometers an hour. I should point out that the end-to-end measurements, they're not until the car stops. They're until the controller single board computer that is on the vehicle, which is a NVIDIA Jetson, receives a message to make the car stop. So I'm not really sure if the speed of the vehicles would be an important factor in the variation of the latency of the end-to-end system. Also, I think given these values, we are not really considering the time it takes to detect the vehicle, because I think we were doing the object detection using 5 frames per second, so that gives you 200 milliseconds worst case for the object detection. So yeah, I don't think, but even with that, it's a pretty high value. So even if the cars were going much faster, I don't think we would see much of a relevant difference regarding those 50 milliseconds, because they're really counting only from the point the detection has happened until the vehicle receives the command to stop. That's what we are measuring. So I'm not really sure speed would be a very important factor in this case.
Thank you very much.
I think there are no other questions, at least online, from the audience. No questions in the audience. Okay. So next presentation is the coffee break. Not your presentation. So we are a bit delayed, so let's shorten it to 15 minutes. So we resume it at 4:15. Okay. For the local ones, we have some cakes and beverages. For the ones at home, so go to your fridge and do the same. So you also have the opportunity to see the videos that we have already on the YouTube channel of the project. So you can look at them now or later. So take your time, and in 15 minutes we'll come back for the second session. That is the other projects presentation and then the joint discussion here in this auditorium. Okay, so see you in 15 minutes.
Limpeza profunda com a nova tecnologia Cif Clean Boost. Cif, naturalmente poderoso.
Hello? Please come. Vamos começar.
Ok.
Fernando, posso?
Estão-me a ouvir bem?
So let's restart.
Ok, Francisco, you can hear me? Yeah.
So
Okay,
the
great.
second session is with the invited projects and one representative of the advisory board, the project advisory board, Paulo Soeiro from Visabeira. So he's going to do his presentation from All Be Smart in Castelo Branco.
Okay, so
Paul, just a moment. There are still some people not in the place. Okay, but please, you may start slowly with your presentation.
great.
So,
So
Paul,
thank you for the invitation. My name is Paul. I'm the founder of OB Smart technology company that is part of this consortium, 5G Auto. 5G Auto is about the development and testing of 5G V2X technology, and is led by Altis Labs, together with the Beira Interior concession Global Via, so A23 highway in Portugal, OB Smart, and the Instituto Politécnico Castelo Branco, and is funded by Compet in Portugal 2020. So as I mentioned, the objective of 5G Auto is to investigate and develop innovative solutions for CITS based on 5G V2X infrastructure. So we are main focus on the advanced V2X based on 5G beyond release 15. So we are looking and taking advantage of the longer range, the higher density, and very high throughput that 5G V2X brings. And this is aligned with the requirements of coverage in Portugal. As you know, by 2025, 95% of the highways should be covered by 5G. So we should take advantage of this to enable CITS services. So one of the main goals and results of the 5G Auto project is a CITS platform system that works as a centralized back office that allows the road operator to configure alerts that automatically will appear on the onboard application or in the infotainment systems. So the communication is done through 5G V2X, and we have implemented several CITS use cases that have been tested. And I'm going to now to show some videos that are the results of the pilot done at A23 highway that is managed by Global Via. So the first video I'm going to play. So showcases several CITS use cases. So this is the Gardunha tunnel, an important infrastructure for the interior of the country. We have implemented several roadside units across the highway, and since part of the project also addressed the tunnel, and we don't have geolocation inside the tunnel, we start to implement these Waze beacons to provide geolocation that is critical for V2X to work. So these Waze beacons provides the geolocation inside the tunnel. This is the very interior central control center, where we have integrated the CITS platform and where the road operators can create alerts in a very easy way. So you can see the infrastructure that was deployed across the highway. And in this example, the road operator will create an event that is roadworks warning, for instance. So there is a roadworks warning in this section of the highway. So we can configure the meters or the warning distance, the maximum speed that is allowed in this area. And in the calendar, you can control when this alert is going to be visible. And then the antennas will start broadcast the CITS messages that will be picked up by the onboard unit and will be visualized by the driver through onboard application. That for testing, we are using, in the first approach, a tablet connected to the onboard unit, and you can see here a real deployment with the roadworks warning in the highway. We work very close with our interior global via that allowed us to do these real deployments. Here is an emergency vehicle that is getting into the Gardenia tunnel. Geolocation is possible through the beacons, as I told you. And here you can monitoring the presence of the emergency vehicle, and we are inviting drivers to slow down and drive with caution. Other use case, an accident, road accident warning. So this accident was configured through the CITS platform, and then the drivers that are approaching the accident area will receive the messages and the distance that you are from the accident. So all these messages are standardized by CITS and we follow the standard. We also participate together with Copernicus initiative by ESA on the integration of our platform with the Copernicus system. So we'd like also to showcase that the CITS platform can also get inputs from external sources and not just by the events that are configured by the road operator. So Copernicus has Europe's eyes on Earth, has sensors that detect wildfires, for instance. This is open data that we integrate with our platform. Just a quick example what is possible. In this case, we are in the interior area of Portugal. There is a lot of wildfires. And imagine that is a wildfire 20 kilometers up front. And this wildfire, the smoke is detected by the satellites from Copernicus. So this technology is available by open source. Copernicus makes this data available. You can see here a map of the Fundão area. And then if there's an wildfire, the broadcast automatically start sending emergency evacuation alerts that invites the drivers to escape from the highway before goes to the dangerous area. Another example, okay, the see-through, the V2X connectivity allows high throughput between vehicles for safe overtaking. We have here an example where the driver is in a rural road where typically overtaking could be dangerous. And the V2V connectivity that 5G allows is going to be tested here. So the driver will switch to the camera of the car that is in front. So this circle, and you can see that if the camera of the car that is in front, and then it will start the overtaking in a safely way. As you can see here, these are two vehicles from Global VR doing the testing. And yes, all these labs also, of course, participates in the and deploy roadside units across the highway that have been used to broadcast these messages that were configured through the CITS platform. What else? Yeah, here integration with the car infotainment system. So far, you have just look at the tablet that we are using for testing. But in the later stage of the project, we managed to integrate the messages with infotainment systems of Tesla Model 3. And you can see here, these are actually the messages received through our technology. So the car is approaching roadworks area before the Gardunha tunnel, and the distance that you are from the different alerts. So this is a new step that allowed us to integrate with a real infotainment system, in this case for a use case related with road alerts. Again, the importance of have coverage. We have roadside units inside the tunnel that allows us to test this technology. Okay, so what else? Interoperability tests are very important. So we participate in several ETSI plug tests together with the 5G Automotive Association. So Obismart as a part of the CV2X plug test vendors. We were to Germany to do testing with different manufacturers of roadside units and providers of CITS technology. This is very important to guarantee interoperability. Yeah, some images of the outdoor testing done in Germany with the big players of the industry. Okay, to finalize, and since today I saw several presentations using open interface, I'm going just to show with our product that is called OEI Box, developed by Obismart, that in part was used in the 5G Auto project, and the idea is to facilitate the use of open interface. You just Google OEI Box, but I will show you how it works. So here you are testing our own Genode B that runs open interface. So inside this computer you have a distribution of open interface that is very well tested by Obismart. Obismart is one of the key contributors to the open interface and a member of the OEI Software Alliance. We have here the core network, the Genode B, running in a commercial PC connected to a USRP, an external antenna, and you are doing here cell coverage testing with real equipment. And also the idea is to test the stability of open interface. You will know that OEI is not easy to use. And our team, after years of using OEI, we launched this product to facilitate the use of OEI. So here you have a cell coverage of 150 meters. You have stability. The code remains open source. So you can see open interface over there with a real iPhone 14 Pro standalone. This is standalone technology for 5G. Here we only have 40 megahertz, so we are reaching 100 megabits per second. Establishing a FaceTime call between two user equipments using open interface. So this brings OEI to another level that you can exploit in your research. So I invite you to use. And then we expose the parameters. So the signal interference noise ratio, physical layer parameters from the core, from the Genode B. In this case, Tiago is moving away from the Genode B, and you can see that the degradation of the signal interference noise ratio. So you see that the cell coverage is around this area, and the signal interference noise ratio goes almost to 0. So our dashboard export data that usually is very hard to get from OEI. Here the OEI lost the connection. Okay, so this is all from my side. Thank you, and I'm open for questions.
Okay, Paul, thank you. So
Great.
we'll keep the questions for the panel, maybe. There's some strange effect in this local screen.
Yeah, there is a strange effect.
Please switch.
I'm going to out, and then I will join again.
Okay, good. Thank you, Paul, again. So the next presentation is from the InsectIT project. The agenda is wrong, so the speaker is Peter Priller, that is not couldn't be present, so we recorded this presentation. And then we'll have in the debate Lucas Kulas. So the name in the agenda is also wrong. So Peter will be remote, offline, and Lucas will be online, also remote, for the joint discussion for the debate in a few minutes. So going for the recorded presentation from Peter. Hopefully audio will be okay.
Well, hello everybody. My name is Peter Priller. I'm with EVL in Austria, and I'm very happy to present you the project Insect and give you a very brief introduction. So, even briefer, a short introduction to where I come from. So, EVL is a large company based in Austria with worldwide subsidiaries, which is in the automotive business, with engineering, testing solutions, and simulation tools. And this is also, of course, our focus in the project. Now, let's switch to Insect. Insect is a large European project which started in 2020 and will end August of this year with 40 plus partners all over Europe. And I guess the best way to learn a little bit about the project would be just to go on the website. You can see the address on the top slide, www.insect.eu, insect with double T. And the motto you can see already on the screen, going to the edge, bringing the Internet of Things and artificial intelligence together. So that's the main thing about it. So Insect, the name, and why is there double T? Well, you see those words on the left side. It's about intelligent, secure, trustable things. Intelligent, well, we see more and more systems, devices, gadgets getting more than just standard basic features, getting something like intelligent. And making something intelligent often is combined with AI, ML, and this is often combined with data, and often data comes from IoT systems, from the environment. Data needs to be secure, systems need to be secure, so this is a very, very big focus of our project. And together with that, it's also about trustability. So when is a system trustable? When is an AI system trustable? This is another thing we work on, both the basic principles as well the implementations. And it's about things, about actually many things in many different domains, industrial domains, where we apply those technologies which we develop in this project. Okay, and this is the main formula when we say we bring together artificial intelligence, AI, and IoT. Then we say it's a new thing, and it's more than just the sum of the parts of it. It's the artificial intelligence of things, AIoT. All right, so artificial intelligence of things. This is something we think is quite natural when the IoT devices get more and more AI either embedded in the system or in combination with something working on the cloud. So both is possible. Why is that? Well, very, very clearly, AI increases the value of IoT, and it does so through making things, well, adapting to the environment, using data from the IoT systems. So it's a mutual benefit between AI and IoT. And AI very often runs in the cloud. We see that, and like ChatGPT, for example, is now more or less well known to everybody. But there are many reasons why AI should also run, or maybe even just run, close to the IoT system, close to the device, so on the edge, For example, to process data locally makes a lot of sense if this is critical data, time critical, but also GDPR critical data. And to a lot of solutions just work that way. Okay, so the idea is that we provide methods, provide technologies, implementations, mature technologies, so those things can get trustworthy. They earn the trust of the users. And we did a deep analysis on what is trust and how is it, how can trust be achieved in systems, and then how can we implement that in AIoT systems. Part of it would be also resiliency, security, reliability. And security and how to test security is also a very important thing in this project. So it's about AI supported in embedded processing as well as AI in wireless transmission, as well as also at least partly AI in cloud systems. We worked on a high-level architecture which was published and which is an extension of industry standard architectures as well as an extension of a previous project which is called SCAT. Unfortunately, I don't have the time to go into details, but we worked on where and how to add the aspect of artificial intelligence in these typical industrial high-level architectures. So there's something to be read on that. Finally, the use cases. So a very important part of the project is that these ideas, these technologies need to be driven by use cases, real-world use cases, industrial use cases. And as you can see, within a lot of domains in the automotive business, where my company comes from, as well as in public transport, in smart infrastructure, aeronautics, airplanes, in public health, manufacturing, of course, a very big sector, smart building, as well as maritime and railway systems. Now, let me give you a very short example of what we do, and actually this is a nice collaboration between ISEP and AVL, and it's about the connected vehicle. So vehicles already do, and in future will even more so do, communicate between each other as well as towards some base stations or some road infrastructure. And this works pretty okay in a free area and rural areas, however, as long as the coverage is given. However, it gets quite complicated in special areas like, for example, inner cities, between skyscrapers, within tunnels and these kind of scenarios. It's very hard to simulate and to model this behavior, and also we work on aspects on how to overcome the challenges, for example, with MIMR systems, and to do so intelligently. Now that brings together all these base ingredients, and the cybersecurity topic is something which AVL, for example, follows in that quite deeply, and how to test those systems towards cybersecurity properties. So where is some specific outcomes of this use case, or from this technologies applied in this use case, is, for example, a better modeling methods, applying, for example, AI ML to make it much more performant, much better in a lot of ways, and most importantly, applicable, so we can use that models for not only simulate the behavior of existing systems, but to improve them, for example, by applying multiple input, multiple output systems towards that, and controlling and steering the communication much better. Well, I'm already at the end of our time slot, so let me come to the summary. Insect is about bringing together the IoT and the artificial intelligence, making it the benefits from both systems, merging them together into the AIoT, the artificial intelligence of things. Together with that, it is even, well, very important build the trust in the AIoT, otherwise it will not get acceptance in the marketplace. So dependability, security, safety, and those properties are extremely important, and how to achieve them. And finally, we showcase that in a broad range of industrial applications and domains in a lot of use cases. Well, I'm quite sorry that I cannot be with you in person, but I hope I was able to give you a brief overview of the project. If you're interested, please contact us via this email address or go to the website. Okay, so thank you very much, and goodbye.
But there is a colleague online that is going to participate in the debate, so the applauses are welcome. Okay, so we continue now with the steroid project. João Silva. Okay, João.
Okay, great. Okay, thank you very much. Hello, good afternoon. My name is João Silva from Vortex Collab, and since we are a bit late, I will just go very quickly, hopefully, over this, just a brief presentation, although most of you probably know us since we've been working in the several projects that have been presented here, both FLOYD, Insect, and in this case, Steroid. We are a research-driven entity whose goal is to do an interface between academia and industry to bring the great ideas that exist in our academia and push them a bit over and increase the TRL so that it becomes closer to production in industry. And our main goals are to work on the safety and security technological bricks and tools for cyber-physical systems, which should be mostly based upon safety and security. So some numbers not very relevant. We have been growing and participating in several projects, which some of them are here present. But let's talk about Steroid in particular. So what is Steroid? What we wanted to have with this Steroid? A platform for verification and validation of autonomous driving and ADAS components. So nowadays, we have been talking a lot about autonomous driving and how the cars are connected and the software on wheels and all those terms and definitions. The truth is, our cars have been having increasing complexity in the software, in everything that they do. And the software for these cars needs to be tested and validated. And so, besides all the existing verification and validation methodologies that exist during software development, there is a lot of extra systems that we would like to understand how they are working and in an integrated way. And when we are talking about autonomous driving, well, it's dangerous to go on the road. It's a lot of logistics to get everything up and running, to get the correct scenarios and edge cases that we want to test is also quite difficult to have. Not to say the danger of producing those edge cases. So what we wanted was to create, to give the tools to create a platform that allows to test and validate what is the end result of this autonomous driving software. For that, we go with simulation. Let's build a simulation environment where we can simulate everything that is involved in autonomous driving, in autonomous connected mobility in general. And we focused particularly in a T-junction use case where we can have a lot of complexity and different scenarios. In this case, we may have an ego vehicle. Let's consider the vehicle that is under test. So basically all of this, I think we can summarize it to let's test and validate a software that is driving the car, a third-party software. So whoever produces a software they want to test how they behave. Let's create a platform that is completely unrelated to do those tests, a sandbox, if you like, to just throw this driver, this autonomous driver, and see how it behaves. A driving exam in some way. So in this case, we had to provide the whole world for this driver to drive in, which is comprised of connected vehicles, of pedestrians, even legacy vehicles, who knows. And the car exists there. In this case, one small visualization of this intersection running. We have several vehicles. So the vehicle that is coming on top is the ego vehicle. That one is being controlled by a third-party software. The other two vehicles and the pedestrian are being controlled by our platform. So it's the world, the NPCs, if you like to make the parallel with the games, are the NPCs that are populating the world, behaving as it was defined by the user. And well, let's see how our driving software behaves, and let's evaluate how it behaves. So to achieve this, we wanted to have, so besides the driving simulator, obviously we need a driving simulator. For that we are using Carla, and I think we all agree that autonomous driving will not exist without communications. So we also needed some network simulator to close all these loops, so that our vehicle will surely, the software that we have no idea what is there, but surely we'll be expecting to have other vehicles communicating with him, sending cams and dems and CPMs and whatever V2X messages. So we also wanted to get this, for simplification, let's call R3 an R3 simulator, although it's a framework, but let's call it that way. We also wanted the user to be able to define the scenarios in an easy way, so let's stick to the existing standards also, open scenario for defining dynamic driving scenarios. Our driving simulator is compatible with the open scenario, so let's go with it. And on top of all of this, we put everything working together. On top of this, let's build our monitors to actually evaluate and validate what is happening. So runtime monitoring with formal methods approach. These monitors are also self-generated by a DSL that has been developed by us at Vortex. So since we have multiple situations, multiple entities here involved, we needed to come up with a way to connect everything, to create a standard way for them to communicate. So we will end up, so why not use ROS, Robot Operating System, which is a great communication framework, inter-process communication framework. And also we need several pieces here. We need to have the Carla simulator, which works as a server. We have the scenario runner, which interprets the open scenario and spawns everything and executes it in the Carla simulator. We have the R3 itself with all the adaptations needed to have this communication with the Carla. Then we have a set of monitors that need to be launched to do the evaluation of all the scenario. So for that we also need a manager that deals with all of this. The idea is to do automatic deployment and to facilitate the continuous integration and continuous development. Hence, we prepared everything to run in batches. So you can imagine we have a directory with a set of open scenario files described. Our manager just gets in there, sees for the scenarios of this directory what we need. I need the simulator, the broker, the R3, and the monitors. These two monitors, okay. Then it deploys everything, runs everything overnight. We can think of it running overnight. In the end, we have the results of the monitors. Let's go for the next directory, next batch of tests. So the idea is to have, or to use this kind of platform within the development cycle, so not necessarily only in the end, but to make it agile, to do smaller increments in the development of an autonomous driving software, which is complex by definition. So another thing, or other scenarios that we have for running all of this live with the Carl and so on, it needs a powerful computer for simulation. We also wanted to integrate it with existing situations that there are several, and for that, even here in Aveiro, we have one of the partners of the project is IT, which has already an infrastructure in place. They have logs of V2X messages. Again, through our ego has happened before. So all of these different pieces, we have it configurable in the batches. So I'm really just finishing time. So in a very quick way, this is one of the tools that we also have, where we have the ability to create even more chaos in all of this. So let's just spawn a vehicle in the middle of that intersection at any time. The user can just open the interface. Let's create a vehicle there, which is a crashed vehicle at some point. All our world, or all of the NPCs that are being controlled by our platform, at this point, if they are within field of view, they should be sending the then messages, so that, again, the ego vehicle software should be expecting them. So let's provide them all of this. Next steps, CPM messages for the sharing of the cooperative awareness, and later on, hopefully also the maneuver messages, the MGMs. So that's basically it in a very fast way. I'm already over time. Platform for allowing us to do scenario-based testing with runtime monitoring, live monitoring, for accelerating the development of AD systems.
Thank you, João. So now we go for next project that will be presented by Professor Joaquim Ferreira from Instituto de Comunicações. He's going to do it from his own laptop. So let's switch. Não está a dar? Esqueci, não dá? Está aí. Mas não está aí, não entra na sessão. Não entra na sessão.
Eu faço a minha. Eu faço a minha e depois temos tempo para falar.
Okay, so we move to the next one and then we come back to Route 25. So it will be Paulo Soeiro from Visabeira. Thank you, Paulo.
Hi, good afternoon. I think I was saying I was going to say I'm the oldest person in the room, but I cannot say that anymore. My name is Paulo Soeiro. I work in Group Visabeira. It is a national group that works in the engineering activities. First of all, I would like to thank Francisco and Altis Labs to give us the opportunity to come here today. So I'm going to give you a quick overview. It's not so technical because then I would have to go into depth, and we don't have the time for it. So very quickly about us, we are a conglomerate group. We have a revenue on the range of 1.5 thousand million euro. So we work basically in engineering, most of all, but then we have some, what is normally called non-related portfolio, like in the industry and tourism. In Visabeira, I work in a company that is, what is there? It's in Portuguese, Visabeira R&D. So in Visabeira R&D, we have 4 different groups working on engineering. One of it is R&D in dematerialization of operations. So just to tell you, we are a big operations company in the fields of engineering and energy. So what we do over there is to, over all of these projects on the left, we do internal projects to, let's say, dematerialize and datify our operations. Just to give you a notion about that, we have about 6,000 different teams that do small services, like going to a customer's premises and install a fiber or a telecom equipment. That type of operation normally is worth 60 to 70 euro. So we do a lot of millions of those to be able to compile all of this revenue that you see over here. So we have a very big data management machine working on putting all of those operations together. And this has been developed by us. We call it the generalized workforce management system. So we have been working on this since the year 2000, so about 20 years ago. This is actually the reason why we are so big in terms of this type of company. Normally, these companies are working on the maximum 30 million euro bracket. We are quite a number of volumes above that. Then we have some advanced manufacturing that you see over there that is basically implementation of SAP MII, Manufacturing Intelligence, so a dedicated module of a third-party supplier. And then you have the ones on the right-hand side, that's the ones that I work in Visabeira. So basically, we do a lot of internal consultancy based on European programs and projects. So we have a number of things over there, like big data, zero defect manufacturing, data quality, CO2 capture, advanced cybersecurity, 5G, all of these projects, each one of them has a core functionality that we're working at. We'll go over it on the next slides. More than that, we are also in the resilience and recuperation program in Portugal from the Portuguese government, where we have we lead the eco-ceramics program. That is a very wide innovation program dedicated to ceramics. In Portugal, it gathers 47 partners, and it's financed on the rate of 120 million euro. Then we have another one that is TextPact. It's for the development of biometrics-enabled vests for professional applications. We do that with the CITEV and CENTI. And then we have the last but not least one on your right-hand side. That is a laboratory that we're just financed to do, also by the Portuguese government, and we'll go a little bit about that one. So about VTEB, so Visabeira, it's Visabeira Test Lab. You see a little bit here about how we are geared in terms of partners. So we have quite big industrial and sectorial partners working with us. Both very old type of partners like AIP, that is almost 200 years old, as well as the new ZLTs and the new DHIs. In terms of service delivery model, we'll go a little bit about this V on the next slide, but we use the normal systems development V. So you have, this is, normally people just use the TRL system just to grade, technological reliability and maturity. But there is another one that NASA uses also for systems development. It is the development V that you see over here. So that basically starts with the idea until what we call RAMS certifications. So RAMS certification is reliability, availability, maintainability, and security on top of on the top part of the V. In terms of user profiles, we have systems and platforms, physical products, digital products, and advanced industrial processes. So it's a very broad field of work. And our laboratory will have, because it's still being built, it will have 7 different key enabling technologies. And we'll go a little bit about that also. So in terms of mission statement, what we have is something that says we'll be creating this multi-technology laboratory capable of testing the latest cutting-edge technologies in technology transfer stage, this meaning ready to enter the market, assuring that they are fully ready for market launch. This means that when they reach the top level, they'll get this reliability, availability, maintainability, and security certification that will assure the people that are going to go to funding stage after testing that they have a product that they go safely be invested by venture capital and reach the market. So over here we'll go a little bit about this our work model. So our work model is, you have on the left the functions that will be done by the startups and companies that will approach us, and on the right hand side you have the functions that will be done by us. So you have on the left hand side the normal when intelligent people get together and they are organized. So you have ideation and concept, setup of development of a bill of requirements, functional development of modules and integrated parts of the system, and then this Fab Lab production that will lead to a functional prototype. All of you know functional prototypes, you know, they're some of the things that are over there, also on top of the tables. We'll pick up over here the functional prototype. We'll do integration testing, this meaning that we'll be testing that all parts of the system work fully together with each one. We'll do functional testing of the system. This means that we'll be checking that that functional testing fully complies with the bill of requirements that was previously set up. We'll do interoperability testing, and this means that today when we develop a system, it's supposed to work with a large number of other systems. So we'll be working on that phase in order to verify compliance, that the system we're testing will be able to work with other third-party systems, and then we'll achieve RAMS certification. So that's something that is reliable, that is 99% available, that is maintainable, and that poses no security risks. This works for physical systems, platforms, and even for the large language models that we're speaking on the interval. So our target systems are systems that are already ready to, they are already on TRL 6, and the goal is to take them to TRL 9. This is again a little bit about RAMS. So you have the typical user profiles, and then the 4 parameters that will attest that the system is ready to go into venture capture capital system stage. Okay, and that's all for me. I think that I gave enough time. So last one, sorry, I forgot about this one. So we'll be over here in Aveiro, in PCI. So we'll have the main hub dedicated to manufacturing in Aveiro, and then a distributed computing IoT over ones, what is normally called smart cities or intermunicipal systems, but it's really distributed computing in Viseu. And I think that's all. Many thanks.
Thank you, Paul. So now we return to Route 25. Hopefully. Okay, so thank you, Joaquim, for presenting Route 25.
Okay, good afternoon. I'm Joaquim Ferreira from the Institute of Telecommunications. I'm presenting the Route 25 project, a brief introduction and then some work that we'll be doing in the project. Route 25 project is Agenda for Autonomous, Intelligent, Interoperable and Inclusive Mobility. It's a project led by Capgemini with over 25 partners and total investment around 60 million euros. So the aim of the project is mostly focused on cooperative, connected and automated mobility and all the technologies around this application area, including assisted autonomous driving, digital experience, connected infrastructures that I will be addressed in a minute, intelligent infrastructure for low carbon intercity mobility, and I will focus also on the large scale demonstrator that will be one of our main contributions at IT Aveiro. So we have different work packages focus addressing all these issues from assisted and autonomous driving for safe mobility to intelligent infrastructures and everything glued by, I would say, the large-scale demonstrators. So we have 3 large-scale demonstrators, one in Aveiro and the Ilha region, another one in Fundão and another one in Porto. So these 3 large-scale demonstrators will host a series of products and services that will be tested in these regions. So some background on CCAM. Probably you already saw these figures. So we have on the top the 6 SIA driving automation levels and the cooperation classes. So we will be addressing the cooperative part and the connected part of CCAM. And we'll be targeting for level 3, level 4, and class B and C, intent sharing and let's do this together, the vehicles cooperation. So going back to the large-scale demonstrator in Aveiro, so we already have large infrastructure in the field. The Route 25 demonstrator will federate the different equipments that you already have installed in the field on the urban areas of both Aveiro and the beaches and connected by the A25 highway. So these deployments came from 2 previous projects, PASMO and Aveiro Open Lab. Then we have a series of sensing and communication units all over the place with a high density deployment in the city of Aveiro with a private optical fiber network and 40 smart lampposts with communication sensing capabilities. With the Route 25 project, we are investing in this region to install new generation equipment, new sensors, and making this more dense deployment of sensors and communication units. We are also deploying a 5G, I would say several 5G cores on the city and on the region. We will have automated vehicles for testing and some other equipment. So regarding the equipment that we already installed in the field, we have different technologies. So we are, I would say, agnostic on the technological side. We have a traditional DSG5 with over 50 roadside units installed and many onboard units installed in vehicles and ready to be installed also. On the 5G side, we have a standalone core with 3 antennas in the field and many onboard units already. So these 5G infrastructure will be extended, and other cores will be also installed in the city. All this network is supporting by backhauling network, also maintained and owned by IT, with optical fiber, both private and commercial and shared optical fiber, and with radio links and many other technologies. On the 5G side, we plan to cover the I-25 motorway with continuous coverage of the I-25 motorway with 5G, and the access to the harbor also, and part of the beaches. In the city, there are also planning some deployment of these 5G networks. In this project, IT will be will interact, will connect to some mobile network operators to test some use cases, but I think that the mobile network operators will not test directly between them. They will test through IT network, I guess. So some things that we plan to do. So this is more connected with my research group. And Aguiar is also involved in this project. I'm sure she has some other plans, but there are 4 groups from IT involved in this project. My group and Aguiar group, Rui Aguiar and Susana Sargento. So we are addressing different parts of this area. So I'll talk briefly some use cases that my group will address. The first one is the maneuver coordination service. So we are deploying this and test this with real vehicles. So we are for the moment we are testing this in laboratory environment, but we'll extend this to the field. We have some work on this. This maneuver coordination is a safety critical use case that implies some form of consensus between vehicles to agree on the maneuver. So, as you can imagine, there are lots of messages to be exchanged between all the vehicles to decide on some maneuver and then execute the maneuver. So we have some work on this. We plan to extend this work and validate on this large-scale demonstrator. Another thing that we are working is making these maneuvers, negotiation, for example, and in the cloud, where we have digital twins for maneuver coordination, where the burden of the communications, you can do it in the cloud and then transmit the actions back to the vehicles. So that's a very brief presentation of our plans for this project. I'm sure other colleagues will have other plans. Thank you.
Okay, Joaquim, thank you very much. So you move back to the agenda. And the agenda is the panel. So I invite the speakers to come to the front. So Paulo, Joaquim, João, another João. Remotely we'll have Paul Marques, that already presented 5G Auto, and Lucas, not this Lucas, another Lucas. Are you there? Hello?
Yes, I'm here. Hello.
Okay, thank you very much. Pedro Santos will manage the session. Okay, so maybe you could join, or?
Should I sit there?
I think so, yes.
Okay.
Yeah.
Should I take the mic? Perfect. Right, sorry. So hello everyone again. Let's head into this panel session with our distinguished talkers. So Paulo Soeiro from Visabeira, Joaquim Ferreira from IT Aveiro, João Silva from Capgemini, and another João Silva from Vortex. Also Paulo Marques from Albi Smart, and Lucas Kulas from the Gdansk University of Technology, so a last-minute change to the program. So I'll make this quick. I'll make 2 questions. I'll try to capture all of you, and then I'll open the floor for questions from the audience. So the first question I would have is about infrastructure, and infrastructure that is needed to have to support vehicular services, right? So we've seen a couple of presentations about describing already deployed test beds in real conditions. And so, but I would, before talking to Joaquim and Paulo Marques, which were the ones that presented that, I would also address Paulo Soeiro and ask him if Visabeira, being such a large group, you do communications, you do construction, have you ever considered looking into this, the merging of these 2 domains and actually considering the construction supported by technology, so for example, highways or some other context? And I would also ask Joaquim to give us a little bit of feedback on his experience of managing a large-scale testbed for vehicular communications, right? Also, Paulo Marques would be probably also willing to pitch in a little bit on that. But more directly for Paulo Marques, I would go into another key aspect of FLOYD, which was the private 5G network. So the idea that as the 5G equipment becomes more softwareized and the equipment itself becomes easier to install, 5G networks become possibly a solution for providing connectivity over an entire private premise, whether it's an industrial facility, a port, or hardware. So I would ask Paulo Marques, what does he think is missing before private 5G becomes a viable and attractive proposition for industrial customers? So that would be it. So I would give the word to Paulo Soeiro and let him know his thoughts on whether Visabeira has considered this merging of the construction and telecommunications side. Thank you.
Thank you for your question. Yes, we are since 2012 speaking with large road operators in Portugal. On our perspective, you do need a very dense 5G network in order to make all of these technologies work. And we've been working on horizontal directional drilling, so a technique that allows for very quick deployment of fiber just besides on the service corridor besides the highways. And we've been, evangelizing the people that are on these large operators that they do need a very dense 5G network. There have been, very polemical questions like, what is the type of revenue that they will get for being used, because it will be a shared infrastructure. All of the operators will be able to use that infrastructure. And there is a very large field of debate if they will have their own infrastructure, and then they'll do infrastructure sharing or network sharing with the operators, or if they'll define other types of sharing with them. The financial model or the economical model has been at the forefront of the debate since 2012. But yes, we have been, catalyzing that discussion heavily because we are an infrastructure developer. And on our perspective, there are now some new techniques like HDD that can help very quick deployment of very dense 5G networks in the road infrastructures. I don't know if I...
No, perfect. I liked your answer very much. Nice to see that you're considering it. I would ask then Joaquim to give us his thoughts on building and managing such an infrastructure and how this relates to Paulo's answer, please.
For us, I would say a nightmare because it's not our core business to deploy large-scale infrastructure and manage them, making them operational over the years. So we have this issue of putting communication devices, not 5G, ITSG5 some years ago in A25 motorway. Ascendi gave us access to their optical fiber, and then in the near future they will give us access to the pipes, so we can put our own fiber. The pipes are already there, so there's no big issues on that. Biggest issues, I would say, is electricity. To have electricity where we want to have it. So we are constrained in the first deployment by the points where we have both electricity and optical fiber. But now we have some budget to extend and to pass fiber, the new fiber. And we are working with Ascendi, with EMT and IP, so because in the normal business model in motorways, they don't own the infrastructure, they operate it, and the owners is Infraestruturas Portugal. So we must ask them if we can use the infrastructure. But for now, they are very open to it. So it's a very challenging task for a research institute to manage this, because it's not our core business. But I think it's very important, not just for us, for research, but to open this infrastructure to companies to test their products and services. So that as this service it's very important, I guess, and to have an important cluster of companies, both national and international, to use this the infrastructure to deploy their products and to validate them.
Thank you so much. So now I would invite Paulo Marques to give us his thoughts on what is missing before private 5G networks are become a more common reality. Paulo, are you there?
Okay, so yeah, I'm here. So starting by the 5G private networks, you know, I think the advantages of using 5G in the industrial environments instead of the typical Wi-Fi are clear. Because the low latency, the support of robotic communications, augmented reality also has important requirements in low latency. Yeah, but the issue I think is mainly related with the cost. So the cost has to goes down and should be comparable with Wi-Fi deployments. And in Portugal we also have another challenge, that is the lack of spectrum for private 5G networks. So only the main mobile network operators will have the possibility to deploy this kind of networks, which limits opportunities for small companies. Other countries, they follow different approaches. The regulator in Germany, for instance, they reserve 20 megahertz, which is quite good. So I think to be enough for most of the applications. And these 20 megahertz are available for the deployment of local 5G networks, so where interference is controlled. So I would say price and spectrum are very, very related. So I don't know if I have time, I can also comment on the deployments of test networks.
Yeah, sure.
What we did here in A23, of course, needs close, as Joaquin also mentioned, so it's very challenged to have this kind of infrastructure. We were very lucky because we have cooperation with Global Via, so we need the road operator with you, actively supporting you. So it was the case of the 5G Auto project. So we are Global Via A23 allows the deployment of now, I think, 15 roadside units across the highway. So this is critical. But I think also the future of these CITS technologies is not going to be short range roadside units based. So we should expect that the 5G deployment that will be mandatory by 2025 in Portugal. ANACOM says that 95% coverage in highways. So it should be the 5G technology that will support these new services. I would say that ITSC5 technology, this kind, is just the first step towards a densification of 5G that will support the more advanced services on CITS.
Thank
I
you.
think it's so. Yeah.
Sorry.
Okay, thank you.
Okay, do you want to say something else?
No.
No? Okay,
nothing
thank
else.
you. Well, if we had more time, I would ask Joaquim Ferreira what he thinks of the just purely 5G solution that was just mentioned, but...
Depend on what, if you're talking to Volkswagen, probably they don't share this idea. But it's, I would say the future is hybrid communications, different technologies. So we have some devices already with the 3 technologies inside, ITS-G5, CV2X, and 5G on the same device. Not on the same module, I would say. But we were in contact with a major manufacturer some months ago, and they were telling us that the automotive market is not an issue on the connected side, because every vehicle that will come in the next 3-4 years will come with some sort of communications. So either 5G or CV2X, ITS-G5, depending on the particular manufacturer. So that's an open issue, I would say.
Thank you, thank you. So we have a question from the audience, so I think we could move on.
Okay, I had another question. The first question then, just relating to what Pedro asked before, is whether in the audience you have seen any proof, practical proof, that 5G can deliver the low latencies, application layer, end-to-end low latencies that they are promising to as a competitor to ITS-G5.
Do you want to address that to anyone?
No, just anybody. Well, the people who were talking about, I would say to everybody, because everybody was being, probably not Paulo Sueiro, because he was not talking specifically about a V2X project, but I think everybody else was talking about V2X projects. And so have you seen proof in your project or in other projects or in the scientific community that cellular, 5G, 6G, I don't mind whichever G, can deliver the low latencies that, I mean, application layer end-to-end, that they are promising?
Sorry, depending on what the 5G are you talking about. Usually I will divide the V2X communications into families. Localized communications, we have ITS-G5 and CV2X, so we have low latency there. If you're talking about networked communication, that goes through to the core of the network, so you will have average, I would say, 50 milliseconds. I don't see results much below that. So I would say for very low latency, I think for the next few years, we have to rely on localized communications, either ITS-G5 or CV2X.
Okay, thank you. Does anyone want to add to Joaquim's answer? No? Okay, so in the interest of time, I'll move forward. Do you want to reply or okay, perfect. In the interest of time, I move forward to the second question, and this will be directed to Lucas and João. We've seen that 5G and edge computing have been a key aspect of FLOYD, and in FLOYD's use case, and I think they probably show up a lot in insects use cases, which are a lot, and so Lucas probably knows many of them. And so I would first direct part of my question to Lucas. From all the use cases that you find in insect, which ones do you think can still or will be transferred to the 5G challenge, right? So use cases that 5G hasn't fully addressed and that probably will be transported to the 6G aspect, and or which new use cases do you think may show up in future as we travel the road towards 6G? And my second part of the question would go to João Silva from Capgemini. It's about the edge computing. So I still struggle a little bit how is going to be, how the edge services are going to be monetized. And I would like to know what's your view in terms of how are companies going to monetize edge services. I mean, there are so many parties involved. There's telecom operators, there's edge computation operators, whatever that is. So I'm curious, how can companies really monetize from edge node services? And the last question for João Silva from Vortex is really, we see a lot of verification and validation applied to individual components or to point-to-point situations like the communication aspects you were mentioning. But as we move forward to this very decentralized future where you will have edge nodes everywhere, pervasive communication devices everywhere, how do you think that VNV can handle with all that decentralization and all that heterogeneity of devices and links, right? Can we really assure, validate the functionalities we want in that such a heterogeneous future? So I would give the word first to Lucas, hear his thoughts on what use cases as 5G not fully addressed and probably will still be around for the 6G development, or what new use cases does the team think that may be relevant or show up in the meantime, given that Insect has so many use cases? Probably you'll have one idea or two about this. And so please, Lucas, if you would be so kind, I'll give the word to you.
Thank you for this question. Actually, it's a very interesting question because in Insect we are covering automotive use cases, but this is the topic you know and the auditory knows quite well. But I think that something really interesting it's to address the places when the money can flow, I would say, easily. Because you will save time and reduce risks. And I'm talking about ports and harbors and logistics. This is, in Insect, we developed a very big use case that is addressing reducing time of operations in ports, in future smart ports. Because in ports, you've got usually quite big areas that are not homogeneous in terms of ownership or operations. So it means that you have many different companies that are renting the space from the port authority. You have a few modes of transport. So you have not only cars, but you have rail and also floating units. You will have in close future also robots, either for logistic purposes, either for inspection purposes. And in ports, I'm not sure if you are aware, the port environment is really difficult in terms of propagation. So even if you use advanced 4G systems, there is spots where you cannot find communication due to a lot of metal, a lot of changes in environment. So I think this area is particularly interesting in terms of revenues, because in ports, and every minute saved, it transfers immediately into revenues, into increased revenues for ports, because then they can serve more different more ships, and they can unload them faster. And also ports are very during these days, especially they suffer from different cyber attacks on physical layers. That means jamming attacks can happen and are happening. So in this respect, 5G and future 6G systems, I believe, could be very handy and provide profits for both operators and providers of different systems, and for ports as well. So this is a field that might be interesting for the people involved in 5G development.
Okay, thank you. I see that the port environment is very challenging, so communication challenges there are definitely not over or not fully resolved, I guess, from your words. Thank you. Thank you for your input. So I will now pass the word to João to tell us how can we monetize edge services.
Okay. Thank you, Pedro. I think, in fact, it's a very interesting question when we are working for edge cloud computing and 5G core to start thinking how it can be monetized and sold. So I believe there are many key factors to be able to achieve that. One of those can be, for example, I believe, marketing and advertisement. I think it's very important to the service providers to be able to explain in a very direct and concise way to the customers why edge cloud computing is important, how it can be an improvement to their businesses, what it can add, let's say. So I will say that as a first topic. After that, I believe also it's important to have some guarantees in terms of performance. So for example, for the service providers to establish some service level agreements that can guarantee some metrics and values for latency, reliability, availability as well. So it's very important for edge cloud computing concept. Also to have a strong investment, for example, in terms of security and privacy of the data that it's used. Also to gain the confidence of the customers in that point, to attract new customers and to keep the customers that they already have. Also, maybe in terms of price models, let's say, to establish some fair price models that can adapt and fit the customer requirements in this case. And also, I'm saying maybe as a last one, but because I believe there are many factors and key factors for this, but maybe to build a very strong infrastructure that it's able to provide all the requirements for edge cloud computing, for example, for autonomous driving that we mentioned today, to have the values for low latency, reliability that are required, which are very demanding. So I believe that these are some factors that are necessary to achieve and to be able to monetize.
Let me just ask you a very quick follow-up question before handing over to João Silva from Vortex. But who do you think will be providing edge computing services? Will be the telecom operators? Will be some different sort of operators? What's your take on that?
Well, in my opinion, yes, I believe it can be telecom operators. It's not defined area yet, but probably it can be one of the steps for that, yes, in my opinion. Yeah.
Okay, thank you. Thank you very much. And so now finally to João Silva. So how can we ensure V2V, sorry, this was a slip on my tongue, verification and validation in a context which is even more decentralized, multi-brand, edge nodes, which we don't fully control. How can we provide guarantees of anything in such a decentralized environment?
Well, hello. Thank you for the question. It's a tricky one, obviously, because I think the way to go, I think in the end we will almost inevitably have at least a few trends, a few different ones. And if we think specifically in the autonomous driving part, we need to validate if the car drivers, the autonomous drivers, are fulfilling are complying with the traffic rules. And we already nowadays have 2 or 3 different sets of traffic rules. So fortunately not that many, but we have at least right-handed driving, left-handed driving, a few differences in the signal types, but there is at least a semi-standard, if we may call it that way, because many things are common. At least for instance, if we think about traffic lights, it's common everywhere. I don't think there is any country that doesn't use red for stopping and green for going, for instance. So I think in the end, standardization will be the key to allow us to do any of this. So we are on the way, and it's a pity that Pedro is not here anymore. On the ITS, he presented a good catch on the current steps, the efforts that are being done both in Europe, and he told us about the three main issues, the three main points where this is happening in main geographies. So I think in the end we will have to rely on that we will reach a consensus, or at least 2 or 3 different consensus that can narrow down all the methodologies, all the techniques that we will apply in order to be able to actively perform the verification and validation of all of it, with little adaptation to these few standards. So hopefully ETI seems to be on a very good way to that point. We'll see how it goes.
Okay, thank you. Let me ask you, Francisco, should we open the floor for questions from the audience, or should move forward? One question from the audience, or is there any question from the audience to any of the panelists?
Locally or online?
Yeah, or online. I think there's... That's a good one. No, but let's perhaps give to Paulo. I think Paulo...
Yeah, just a very provocative thing about monetization. Okay. So monetization will require, let's think that users of these systems are new users, that are not people, are machines, that it will have to be a very pervasive infrastructure. It will have to cover the complete road infrastructure. So I think monetization will go towards a model of having a new operator for 5G corridors on highways that will have his own model of monetization, just like today we have Vodafone and Altice and so on. So I think there will be an upcoming operator for this type of special mobile.
That's a very interesting view.
I have a provocation for your provocation. It's related with the road operators. So we have the telecom operators we have the telecom operators, and we have the road operator that can have sensors, specialized sensors, to extend the field of view of the automated vehicles. So we have, and then want to monetize these sensors as well. So we have two operators that want to monetize.
We have one question also from Anna and Joan. But maybe Anna's is a follow-up to this one?
I think I can just ease up, but what I wanted to ask is what you think if it will be possible to have autonomous driving, okay? Because we are talking about using 5G to complement autonomous driving and to aid autonomous driving, okay? But then we have all these constraints and also regulation. Do you believe that we are close to having autonomous driving in Europe, and especially in Portugal? And yeah, I would focus mostly on 5G because currently only operators are able to make use of the spectrum. And even for R&D purposes, it is a little bit difficult to get some small band for a project. So it has to be in an area that is to be requested before. So I would only want to ask you about this. Yeah.
Are you directing the question to anyone, or?
I think it's open. But
okay.
I think that most, or probably Joaquim, Paulo, and I'm for Paulo also. Okay. Yeah. I might be able to answer.
So succinctly, are we close to having autonomous driving, and whether 5G is there to support it?
Yeah.
Okay.
And
yeah, sure, because of the standardization issues. So anyone wants to reply to that?
So the reality is autonomous driving is inevitable and unavoidable. It will happen. It is, as you know, for instance, Teslas don't work with this type of system. So in their case, 5G will be an add-on system or an aiding system to their own system. They have the Optimus system, that is a large neural network that works in a centralized way, and there's like an applet in each car, okay, and they get updates all the time. So they are not yet close to level 5, but of course they will get to level 5. The issue now with standardization, so we'll have autonomous driving that is machine-based, not human-based anymore, and then you have 5G add-ons, right? Now, the problem is, at a certain point, lawyers and regulation will come in, and the big questions will come. When an accident happens, who is responsible for damage? Yeah? So that will cause a lot of entropy that will ultimately, like, you know, always humans do, will find a way in which we'll have someone with kind of a proof of authority that will come in and solve the issue in formal terms. But yes, level 5 will come, and this is only.
I would say that the answer depends on the person you ask to. If you ask to a software engineer, they will reply, okay, in 2 years we have automated driving. If you ask to a safety system person used to deploy airplanes and trains, they okay, 20 years. And okay, but you'll be somewhere in the middle. And you also have the different perspective. In the United States, the burden is on the company side, that have to prove that their system is safe and their responsibility. The regulation is somehow a bit more loose than in Europe, where there are very strict regulations. And I would say Europe has the risk to become lagging on this technology because of regulation. Okay, but the regulation and the lawyer's issue, as long as you have some insurance company that accepts the risk and they certifies and the risk is shared, so it's okay. But I would say, if I have to put, now you also have 2 levels. You have the automated driving, where the vehicle only relies on their internal sensors, and that will come. It's operating in the United States already for some years, I would say. But when you're talking about cooperation, that's another business. So cooperation, we have to trust another guy, sensors from other manufacturer, probably sensors from the road, and that's a different game. So that would take much longer, because I think automotive manufacturers, they don't even want to hear about that.
Okay, thank you. Thank you very much. I think it's time to thank our panelists. So a big applause to them. Thank you, and now I pass to Francisco.
Okay, so also thank you from my side to the panelists. I think the questions raised and the answers were quite interesting. So to close the session, we are going now for the final presentation, keynote speaker, Peter Stinkist. Okay, so that's it. We are seeing the program. So switching to Peter's presentation. So thank you, Peter, for coming, and to close the session. Okay, thank you very much. So I'll give you.
Hello. Okay. Okay, so yeah, it's a pleasure to be here. I'm clearly the person responsible for making you late, but I will talk about a research project. And so this is a little bit different from the panel, which was clearly talking about big projects. These are a small project, but I think there's some interesting lessons. So the question that I'm actually interested in is the last one of the panel's topics, which what is really the edge going to look like, right? And so everybody knows, of course, it's 5G, at least for a little while, and then we'll switch to 6G, I assume. But this is a picture that I use in class and so on. It basically tells us something. It's from an ITU document that kind of has a performance goals and so on. But basically what it does is it basically identifies specific metrics such as peak data rates, the user experience data rates, which are also important, and then also latency, which we know is a kind of historically been a sore point for cellular, but is obviously getting better, as we know. And so on the other side, the research community and also industry already has realized that edge clouds has a big advantage if you want to do, if you want to use clouds for applications that have low latency requirements. Okay, and so because you basically bring the computing to the user rather than having the user send its data to a far, far away computer. So what we're going to look at here is a question of vehicular edge offloading as a way to just kind of look at where there might be problems remaining when we try to deploy offloading in general onto an infrastructure that includes 5G type of networks, not specifically 5G, but networks that have goals and some level of indications that they can offer low latency and high bandwidth performance. And also the impact of edge computing in that domain. And so this is, the focus here is going to be the sensor-driven applications, such as some of the things that are associated with autonomous driving, but it's not specific to autonomous driving at all, and low latency constraints. So, as I said, application, sensor inputs, and generating input for a user, which can be a human, interactive applications, or another application that uses the input. I'm going to talk about two classes of applications that differ in what type of state they deal with, and I'll explain exactly what I mean by this when I talk about the application. It's a little bit easier, and I'll talk about two classes of applications. I'm going to skip a lot of the details given the lateness of the hour, but when you're looking, if you're looking at applications that run on the vehicle, there are basically three ways to realize these applications and make them happen. The first one is you execute it on the vehicle. The second one is you take the inputs, send it to the cloud or an edge cloud and get the result back. So you're basically picking a place, either the vehicle or the edge cloud. The third one is partitioning. Okay. The first two are perfectly reasonable for a large number of applications, but for some applications that have high volume sensor inputs, you also run into the problem that communication latencies, not the RTT, but time to send data, is in fact a big factor in the response time to the application. Okay, and in those cases, you may in fact have to do partitioning of the application, where you run part of the application on the vehicle, part of it in the cloud, and that's the case that I will focus on. Collaborators, this actually is a project that was done jointly with General Motors, so we kind of have a car manufacturer's view on this, which is actually a little bit different from what we have in the room, I think. And then I have a bunch of talented people who worked on this and who did a lot of the heavy lifting. One of the reasons why General Motors told me that they are interested in this type of project, which is obviously not mainstream for a car manufacturer, is actually very simple. The idea of putting giant computers in cars is not exactly attractive to them. It's expensive, okay? And so being able to offload is a big advantage to them, potentially, if it is possible. There's a second reason, which hasn't come up yet. According to my collaborators at GM, the average lifetime of a car, including second-hand market, is 2 to 15 years. In other words, you can't look at the road and see only 2022 car models. That's not how it works. There are cars on the road that are 10 plus years older. So you're going to have a very diverse set of vehicles on the road in terms of computing capabilities. That's scary to them, okay? All right, so I'm going to start with something very simple. There is a class of application called data analytics applications. So it takes a sensor input, in this simple example it's video, and it just needs to analyze this sensor input and come up with a simple answer. In this particular application, the is very simple. You want to have a driver be driving. They don't like the song on the radio, or on their that they are playing from their phone, and what they, instead of taking their eyes off the road and pushing some buttons somewhere, they just want to be able to do this to indicate to the car that they don't want to hear this song. Okay, so what happens is basically you have a pipeline of processing going through, starting with a camera feed that records that you're going like this, and then the answer that pops out is switch to the next song. Okay, that's basically what it is. It turns out there are many applications in this category, and they share the same structure that I have here. There are two features that are interesting. The first one is, if you look at the amount of data that is being passed by the stages, between the stages, it shrinks as you move down the pipeline. And it shrinks very quickly. Okay, so that is really good, because this suggests that offloading is potentially a possibility in the sense that doing it all on the car is probably not desirable, because you're sending a lot of data to the cloud or the edge cloud. And so maybe some degree of offloading is needed. The second one shows another advantage of offloading, which is that it's to be expected that if you have a real edge cloud, okay, that it's going to have more powerful computers and servers than what you have sitting in your car. And so by offloading, another benefit is that you get faster execution times. On the other hand, if you have to wait forever for the network to deliver the data, then you've lost all those benefits. Okay, so that's kind of the key idea. So it turns out, and I'm not going to go into the details, but it turns out this is a very easy application to offload. You basically have some estimate of your CPU cycles available, of the network bandwidth available, and you can decide which modules to do locally and which ones to execute in the cloud. That will give you the best and quickest response time. It's fairly straightforward because this very simple structure of the application. And so Ashwin, who did this work, obviously worked on this, did this for a bunch of applications, and showed a bunch of other properties. This actually shows some results. Don't have too much time to talk about these, but one thing that I do want to point out is that he basically ran experiments driving around in a real car waving his hand, okay? And so you're seeing here the results. The darkest color here is if you execute it locally on the vehicle. So that's a less powerful computer, so that turns out to be problematic. This is when he was driving the car in areas where there was a 4G connectivity. Okay, so research was about 5 years ago, and so what you're seeing is that you get a nice benefit over the local execution, but then when you're in this is the 3G connectivity. But then when you're in 4G connectivity, you immediately get a bump already because the communication costs are lower. So what the cellular network does is relevant, okay? It impacts application performance. So that's good, right? So 5G should make this even better, is the short answer. Okay, so now we're going to switch. So the reason why this turned out to be very simple is that in most cases, if you can offload, the amount of state that the application has that has to be transferred to the edge is small. That's why this works very well. So next, GM kind of really surprised me by suggesting that we work on a different application. It's something called SLAM. Now, I'm not sure we have too many robotics people in the room, but SLAM is basically a very different type of application. What it basically does is, if you're moving around, like driving or walking, and you have a camera, stereo camera in our case, that looks forward, what it does is it continuously calculates your current location and which direction you're heading. Okay? And so the way it does that is by using stereo vision or LiDAR to basically compare the frames in a video and to see how particular features, so easy to recognize boxes of pixels, how they shift in the frame over time, and then you basically do triangulation based on that to localize yourself, okay, and to change your identify which direction you're heading. So the details of this work aren't really all that important, but this is basically the application that they chose. So stereo vision. So you basically have a stereo video stream. So that's a fair bit of bandwidth. And response time matters if you would use this for autonomous driving. Okay. And so this is basically what we did. So the goals here are that we had a existing open source SLAM implementation called OrbSLAM, and our goal was to basically find a way of distributing this so that we get a performance that is hopefully almost as good as the monolithic version that you would run on a server. Okay, that was basically our goal. So so our goal is not to improve SLAM. Our goal is to basically distribute it and not lose too much in performance. So I'm going to give you a very brief overview of how this works. But basically the way this works is that there are basically successive frames are used for localization, the way I described it. You see how the little features in the video frame move around and use triangulation to localize yourself. This is called tracking. This is very efficient, it's very fast, but it is subject to drift, which can be quite significant over time. Then there's a number of optimizations that can be performed. One that is especially important is something that is called loop closing. And how it does it doesn't really matter, but the key idea is important. Imagine that I leave my garage to go to work to CMU. I use SLAM while doing this, and then I turn around, and in the evening I go back home. By the time I get home, I know for a fact that I'm physically in the same location as where I started. Okay? The problem is that due to the drift, this is not exactly where SLAM may think I am, right? If this is where I started, due to continuous drift, SLAM may actually think I'm here, which is clearly very wrong and very dangerous, okay, if you would use that output. So what it basically does is it does an optimization where it says, look, we're going to just use the fact that we know where we started, and so we're basically going to move this point over here, and all the intermediate points on the curve, on the trajectory, are basically adjusted, and you effectively distribute the error that you have across all the points on the trajectory. That's how this works. Now it turns out this is a little bit late because you're already back in your garage, but this information is stored in a large database of pre-stripped data that now can be used by SLAM to optimize any new and future trips. Okay. The main point I want you to take away is one thing. Having access to this previous trip data is very important for accuracy because it really, really, really shrinks the drift down to very, very little. It adjusts for it continuously. That's the only takeaway for this. Okay. The drawback, you have a very large pool of data that you need to have access to execute SLAM. That's the drawback. Okay, so now we want to partition this, so we ended up doing some benchmarking. It turns out tracking is very fast. It's done for every frame, and so this is obviously something you want to do on the car. Okay, so this is kind of a no-brainer. The local mapping is something that looks at groups of frames, and so it's a little bit slower and takes a little bit more compute cycles. Okay, but it is actually quite important that you do that because it does already initially help with drift. And then finally, loop closing here is not the actually loop closing itself, but it is using the large database of previous trip data. Okay, and that's not done for used for every frame. That is only used periodically. And so that's actually much more expensive. And you see kind of the whisker plot here. It's hard to predict how long that's going to take. Okay, so that's kind of what we have. So based on this results, we decided to basically execute tracking and local mapping on the vehicle and to do the use of the large database in the cloud, so or an edge cloud, so that we basically don't have to do this heavy processing on the vehicle. So here's what we end up with. Remote mapping, which is effectively a new module that uses a bunch of optimizations, but primarily uses the previous trip data in the cloud at the top of the picture on the right, and then we basically have tracking and local mapping on this. Now here's the question. Where do I store this map? Okay, because it turns out that the way SLAM works, there's supposed to be this large database with all the data in it that is being used to, by all the modules in the system. So large database, okay? And so where are we going to keep this now? Because given that we've partitioned our application. So there's a strong argument to be made that, you know, the previous trip data should be stored in the cloud because that's where the remote mapping happens that uses the previous trip data. Okay, that seems pretty obvious. The current trip data is being used on the car and is being generated on the car, so well, obviously you'll keep that on the car. And now the obvious problem is that the whole point of having the previous trip data is that it is combined with the current data from the current trip, all together nicely integrated. But if you keep it on two different computers, that obviously isn't happening. Okay, so the question is, how do you deal with that? Okay, we need a big single shared map. And the answer is, and this is where I'm going to go very heavy on the skipping details. It turns out we moved ahead with two maps anyway because there is no other way to solve this problem. The data structures are very complicated. Any existing work on consistency between two computers of data completely does not apply here. Okay, so we actually have two maps. We have the local map, which is on the vehicle, and it only contains information collected on this trip. Okay. And then we have a global map, which includes the previous trip data, which is only stored in the cloud, which is kind of the decision that is forced on us. So the question is, how do we actually make this integration works? The way it works is the following. Well, I'm not sure I want to walk that far, but if you look at the right of the figure there, some of the frames that are collected from the current trip are in fact being sent to the cloud, but it is a small subset of the frames. And, oh, okay, we have a mouse. Oh, maybe we have a mouse. Oh, here's the mouse. Okay, so some subset of the frames is being sent from the vehicle to the cloud. And then what the cloud will do is it will take these frames, and we're talking maybe 1 out of 10, maybe 1 out of 15, 1 out of 20, very small percentage. And it takes these frames and it basically uses it to localize and calculate the pose, which is the location and the direction of the vehicle, using the previous trip data. Okay? While doing that, it also takes that information and integrated it, merges it with the previous trip data. Then it basically comes up with its definition of the pose, its decision on what the pose is, and it sends this back to the vehicle, okay, over here. And then what effectively happens is that the car gets this and it says, look, according to the cloud, okay, or the version of the remote mapping module on the cloud, I need to be in location X, which is based on previous trip data and should have high accuracy. It compares it with its estimate of the location, and it always discovers they're not the same. What it does is it accepts the location provided by the cloud because it's based on accurate previous trip data, and it adjusts its entire data structure to account for the error. So it, okay? So it basically periodically gets some feedback from the cloud. You're off by this much, and then it adjusts its data structure. So it effectively learns from the previous trip data that exists in the cloud. Okay, so this may sound like magic, but this is actually works. And so the key issue here, of course, is now, okay, good. We have this working, and now what's the performance of this going to be in a real system? Okay, so that's what I'm building up to. I'm going to skip this. I have just one set of results here that shows how this works. I'm just going to pick one of them. There's a bunch of optimizations that are not really crucial, so I'll skip those. But here, what you're basically seeing is, this is the frequency with which you send frames up. You know, let's say every 10 seconds here, every 20, etc. And what you're seeing is, if you send up the frames very, very frequently, like here, you actually get a relatively small error here of about 1 meter. Okay, relative to what the monolithic SLAM does. The problem is you're sending a lot of data, okay, which is the red bar here. And then as you increase the period, okay, you're seeing that the error goes up, but that obviously the amount of data that you use goes down. Okay, so you get exactly the result that you want. One of the things I want to point out, in practice, we don't use a fixed period. We adjust the period over time based on various things. So if in reality the period is not fixed. Okay, so now I'm moving on to the question that is really the more interesting one, is what did we learn from this, other than, you know, we can actually parallelize SLAM. So I want to get back to this and kind of see how latency and network performance comes into play here. So this is a graph from the paper that Kwame put together. And so what it shows on the right, and this is a little bit hard to read, but again, there are two y-axes. There's one on the left and one on the right. The one on the left is basically what I call latency, okay? The latency here is effectively the response time. So when I send up a frame from the vehicle to the cloud, how long does it take before I get the response? That's an important number, because in that time window, the car is using the wrong pose information. Okay, so this is an important number. So what we're seeing here is then that time goes up, and the x-axis is the round trip time. Okay, this is artificially generated. Obviously, we go a little bit high with 400 milliseconds, and certainly with 5G, you're not, you know, obviously you're in the wrong order of magnitude there. But the so what you're seeing is that as the round trip time goes up, you know, the response time goes up. The white part of the bar is effectively the compute time, okay, and the pink part of the time is effectively the communication time, the time that you're waiting because the network is sending bits, either one way or the other, no, way up, okay? And so what you're seeing is that the response time here of, or how long you have to wait to get a correction to your current pose is actually depends fairly strongly on the RTT, which is not entirely surprising, you would guess, but it's actually quite an increase, okay? And so we use different strategies, but the results are consistent, okay? Now here's an interesting thing. This is not using 5G at all, okay? This is just, we're just running this over an Ethernet, a 1 gigabit Ethernet link with literally the two computers, the server that represents the cloud and the laptop that represents the vehicle. They're just literally in the same room, okay? So we could potentially go as fast as a gigabit on this line. So the question that I'm going to ask is, how is it honestly possible that to send one frame, which is half a megabyte in this case, this is a very old sensor input we're using, takes 1 second to send from a laptop to a computer at a link that supports hundreds of megabits per second? That is just really bizarre result, okay? So how is that possible? Because obviously I think a gigabit Ethernet line is gonna be faster than 5G in terms of latency, right? And now we're obviously adding artificial latency here, but it has more bandwidth than what your average user can expect in 5G. So, okay, so let's go look at this. So we looked at this and considered the fact that in reality, what we have been working on is an application, but the Ethernet cable is way at the bottom of the stack, right? And so the unfortunate thing is that what the application observes is not just the Ethernet cable in our case, or 5G for the scenarios we've been discussing here, but it also observes all the stuff in the middle. That also impacts the performance of the network, because the network is the entire protocol stack. Okay? So let's look at this in a little bit more detail. So SLAM, 5G, and so we have all these layers in between. And so when we started to look at this, what we saw was that there's a little bit of a disconnect between what applications people care about and network people care about. Okay, and so I actually consider myself a networking person, so I'm kind of in the wrong here as well. So applications care a lot about something called flow completion time. So let me first explain the graph. this particular scenario, what we have is we're basically sending a request, which is a video frame. Okay, so that's a large block of data. And then there's computing going on here. And then there's a response that is sent back, which is actually quite small. So this is not exactly to scale here. This is what the networking people call the flow completion time. It's basically from when you send the first bit until you receive the last bit of this particular transfer of data. The flow completion time here is for a 0.5 megabyte video frame, which is not a lot of data, let's be honest, okay? So it turns out that what you saw in pink in the previous graph is this, the time to send the video frame, okay? And it was quite substantial. So what we're seeing here is that from an application perspective, they actually care about the response time, but the flow completion time can make up a substantial part of that, okay? If you then, okay, so that's what the application people care about. Networking people, they care about packets. Networking people don't care about flow completion time. They care about packets, okay? And so if you would actually ask the application people, you know, what about packets? Do you care about their performance? And then they go, no, we don't care about that. We care about the flow completion time. So for those of you who are, you know, look at networking above the 5G layer, what networking people talk about is things like having applications that send packet bursts. They are bad applications. Applications have to do packet pacing. They have to spread out their packets over time, send at a constant bit rate, and so on. TCP fairness, a big topic in the research community right now, and it has been for a long time. The focus is on packet level fairness, okay? So those are the some of the kind of the gap that I'm talking about between what networking people and application people care about. So let's talk a little bit about the different layers, and I'm going to keep this very quick. The first one that I want to focus on is actually the IP layer. But the same is to some lesser degree true for data link, but one layer is bad enough. So let's basically look at flow completion time given a model that would be an idealized view of how protocols such as the IP protocol should work, okay? So basically what they will do is the following. I'll explain this colorful picture here. I have three applications sending a flow, sending data from, let's say, Pittsburgh to Porto or Aveiro, okay? And so there's a brown application, a blue one, and a green one. So what's really happening here is that if you're looking at, this is basically the first packet, this is basically, oh, sorry, this is the first packet that is being sent, and we have nicely interleaved the packets of the different applications because we want to be fair to the application and give them equal bandwidth, okay? Packet level fairness. So what I have is there are 4 packets that make up this particular chunk of data, okay, which is obviously not a lot, but it's all that fits on the slide. And so if I now look at when the application has the entire chunk of data, all 4 packets, what is basically going to be here, oops, this disappeared. It's basically going to be here for green flow, blue flow, and brown flow. And so what you're seeing here is that you made the flow completion time as high as possible. You've maximized it. Well, that's a little bit odd if you give this to an applications person, because they're going to say, wait a second, this is the wrong thing to do. We want to have this go down, okay? And so if we do flow completion time without interleaving, and we're just kind of pretending that we can do this for now, what you can do is you can say, look, I'm first going to send all the green packets of this particular chunk of data. So the green flow is happy very quickly, the green user. Then I'm going to do blue, and then I'm going to do brown. And what you're seeing is that the average flow completion time has gone down, right? What? Is there something wrong? Yeah. Hello? Yeah, we're back. So the average flow completion time has gone down. Now you can look, well, what does this mean for fairness though? Well, the good news is that the brown user is no worse off, okay? the brown user didn't lose performance, but the other two users basically benefited, okay? And so the other thing is that if you really want to worry about fairness, maybe you should be worrying about fairness at the data chunk level, not at the packet level. That's kind of ideally what you would like to do. So next time, when they send data, the brown user gets to go first, and the green user gets to go last. So that would be kind of the ideal scenario. That turns out to be a little bit hard to do in practice, but you know, it's kind of a model. It actually turns out that, oops, what's happening here? Yeah, okay. So it turns out that I didn't discover this problem. This problem has been known for a very long time. In fact, people in data centers worry big time about this, okay? And this is part of the incast problem, which is a well-known problem in data center networking. And so the problem that they're having here is they have a lot of servers sending data to users, and so the flow completion time is very important. You want to see your web page, right? And so if you interleave this data on this link here, you maximize the flow completion time. It's exactly the same problem that we're having and I discussed earlier. And so it turns out that people have known about this. There's actually a solution for that. You can actually do, there are scheduling algorithms that allow you to kind of control how many flows are being served simultaneously, okay? And so this is used inside data centers. I'm actually not aware of this being used outside of data centers, but maybe it should. And actually there is actually a recent Connex paper, which I actually enjoyed reading, which does something somewhat similar in the cellular world. Okay, so it's a little bit of a hard read, although for this audience it's probably easier than it was for me. Okay, next problem, TCP, okay, my favorite topic. Why is low RTT important? I'm going to argue first that it is not important at all. TCP is a transport protocol that does reliable packet transmission, okay, and so the way it does is it doesn't send one packet, wait for an ACK, and then send a second packet. It pipelines packets, right? So it basically sends packets over time, and it fills a pipeline. So the key idea is if you have something like this here, then going from Pittsburgh to Chicago is obviously a bit faster than going to Avero. And so what's going to happen is that if the available bandwidth on the network is the same in both cases, it's going to send packets at the same rate. Okay, that is what pipelining means. The actual length of the pipeline in terms of latency doesn't matter. So why isn't this working? Well, it turns out that TCP has a little function called congestion control. And so I suspect there's a lot of people in the room who may not be familiar with the details, but you would imagine that the rate of a transmission is controlled through a number that is expressed in packets per second. That is not how it is expressed. It is expressed in packets per round trip time. Okay? And you start with 10 packets per round trip time, and then there's an algorithm that increases this. Now, if you have a low round trip time, then you are going to start at a much higher round trip time than at a much higher data rate than if you have a high round trip time. So to a large extent, the problem here is not fundamental to the network, it's caused by TCP. Okay, so that's actually one of the big reasons why we're seeing this very high delivery rate for higher RTTs. So if you would just run, so basically somehow avoiding this problem is important, and that will allow you to live with somewhat longer RTTs and be a little bit less obsessed by this. Again, it turns out that the data center people have figured this one out, and so they are basically very obsessed with latency and very obsessed with not having these long startup times and having the rate increase very slowly, okay? So there's a lesson again to be learned there. And then I have another link on the wireless layer, but I'm just going to skip this because I'm pretty sure that the physical layer people in the room here are well aware of this. So in the interest of time, I'm going to skip this. So wireless links are always tricky, so this is actually old work. But as I said, I'm going to skip this, except there's a lot of animation. So that's kind of some of the things that we learned, right? So So anyway, I don't have too much doubt that 5G and edge computing is going to be the future for the near term. I don't think we need to necessarily focus entirely and limit ourselves to autonomous driving, though. There are other reasons why you might want to do offloading and use edge clouds, okay? So there's the question of how edge computing, what it will look like. That itself seems to be still a debate. I'm a little bit surprised by that. I personally actually think it's going to be real small data centers that aren't sitting on lampposts, but are actually physically somewhat close to where the action takes place, the applications are running, okay? And so the real question is in the networking, because the reality is we can't just run applications directly on 5G. We need the stuff in the middle, okay? And so I think we just need to do something about that and start to think about the full protocol stack than just the bottom one and the top one, right? I really enjoyed the last part of the discussion of the panel, actually, because a big part that comes into play here is what the relationship is between the different parties that exist at the edge. Data center networking people have figured all this stuff out, but they own the servers and they own the data center network, and they have their own implementation of just about everything that they're running there, okay? They don't just run the stuff that you run in the regular public internet, okay? That's not what they run. In fact, all large cloud providers have their own private wide area networks. They don't use the public internet that we use for all kinds of stuff. They have specialized wide area networks to cut back on latency, okay? And so, no, in the edge, we're not just going to be able to just download a standard Linux release and get good performance. I don't think that's going to work. So looking at the relationship between the different providers is, in fact, I think, a big part of this of the problem, because yes, historically you have a cellular provider, you have cloud providers, right? You have maybe a service providers that provides autonomous driving services and other services. You know, there's kind of like, well, somebody has to build the car, right? They have to build the sensors. They're not going to be the same in all cars. So there's a lot of players that come into play here, but that's not necessarily my area of research. My focus is on the network. Okay, thank you.
Thank you very much, Peter, for this quite interesting presentation and raising some interesting aspects that many of us have not thought about. So I'll give the floor for questions. If someone from the audience or from online. Okay, Anna has one question.
I have many questions. I have a lot of questions about this, but we should make a project about this. But the main, or maybe for mine, is these data center networking solutions that you mentioned that solve many of these problems. They are not standardized, as I understand. They don't use standard protocols, as I understood. One thing about the internet is that people agreed on standard protocols that sort of served everybody. So my question is, what would be, can you assess the effort of bringing this, or at least parts of it, to standard, or sorry, to interoperable world?
Yes, I think that's exactly, that is a big part of the problem, actually. I'm glad you pointed out. It is not standardized what they do in data centers, and the problem, of course, is that for the data center operators, you know, like the Googles and the Facebooks and so on, they, for them, this is one of their areas where they can innovate, right? That's where they can get an edge, okay? And so, yes, it's also only runs in their data center, okay? And so they do crazy stuff, and yes, it is going to be very different, right? The problem is you could standardize it, right? Also, there are, in fact, in the public internet, many versions of TCP available, and they all use different congestion control algorithms, and there are ways of making that particular thing work. It's a little bit limiting because it basically means that the congestion control is entirely done on the sender and without help from the receiver. the big difference, which I think you're implying, and I'll just make it explicit, if you would think of each edge cloud with its wires or wireless links to vehicles as a little data center, that would be nice, right? But if it's then operated by different people running different versions of TCP and you're driving around in your car, well, that's going to get very interesting very quickly, right? So yes, but maybe it should be standardized. But there is a question of, you know, can we effectively not just straightforwardly use what the data center people do, but can we learn from it and then adapt it, because it will have to be adapted. Yeah.
Then I have another question, which is, this congestion control research, I don't know, holy grail, is driven by this fear of congestion collapse, also by this multiplexing of many flows going back and forth in a fully meshed network. Mm-hmm. When we think about edge computing, talking to the clients, you do not have a fully meshed network. You have a much more tree-like structure where everybody is probably talking to the same data center. But first, you don't get that. I mean, it doesn't never explode or grow to millions because it's local. So you have this locality issue that Joaquin was talking about earlier. So if we put this local, is then congestion control such a huge problem? And if it's not, do we really need TCP?
Well, I think the reality is, if you look at what they use in some of the data centers, it doesn't look like TCP, right? So the answer is that not necessarily, right? So also, I'm not sure that, so TCP, things like error recovery and so on, these are all probably kind of okay, right? It's really the congestion control that is the big thing. The congestion control that we use today in TCP in the internet is defined on the principle that for every destination, you have no idea what the round trip time is, and you have no idea what the available bandwidth is. You know, if I'm sending to an edge cloud, it looks like I at least have a clue about some of that, right? And so there's certainly some assumptions you can make, and that's also what's actually being used inside data centers. They know the latencies are going to be measured in milliseconds, and really, you know, milliseconds, it's a horrible number for them, right? So I think that you need to look at something. Yes, I think we need to look in that direction. In reality, the cellular network will also be used to access the internet itself, or remote clouds, or whatever, right? So you really have, maybe you can look at it as two trees that, you know, then, you know, are overlaid on top of each other in the cellular part of the communication, right? And then I know one of the things you're also interested in is what are the security issues, right? So the overhead associated with that, given all the parties involved, right? So that is actually another issue.
Okay, there's time for an additional question.
I was going to ask something, but you already kind of some sort of answered the question. I was going to ask you, you talk about network, you call yourself a network people. And you said, okay, so it seems like edge cloud doesn't work really well with our OSI stack concerning the internet. If you call yourself network people, I was going to ask you, okay, we have the TCP, which will be the transport protocol, or UDP, and we will have the IP protocol stack. Between the both of them, which will be the one that you will focus on for changing concerning this new edge cloud instead of the normal internet network infrastructure? Because of the way you talk, it seems right away that you're going to mention the transport protocol instead of the IP. That's the feedback that I get.
No, I think there's two layers that you really need to work on, right? So the first one is the reliable transport and the congestion control. Okay, you need to work on this. Note, by the way, that I have no problem with the protocol stack by definition, especially if you're going to have a mobile device that talks to a lot of different operators. You need a standardized protocol stack. Okay, so let's be honest about that. So you do need to address, I think, the TCP problem as it exists in the public internet, because it introduces, you know, it really penalizes you for latency too much. And the latencies are not just the 5G part. There is more to the internet than 5G, right? So any kind of queuing that happens anywhere is also going to impact your performance. So that's the first one. The second one is the fact that the kind of trying to interleave as nicely as possible. That's the second one. That is actually something that is easier to manage here, because ultimately that's kind of controlled by the base station, right? It controls who gets to send when on the network, and so it is in the best position. That's actually what the paper I referred to is based on. So it is basically in the position to try to reduce the burstiness. The key idea is very simple. Instead of having 100 cars send data at the same time, kind of say, okay, U5 can go, and then U5 you can go, and U5 you can go, and it has more of a longer-term window that it uses to be concerned about fairness, okay? And so that, I mean, I'm obviously oversimplifying this a lot, right? But those are really the two issues you need to really worry about, because these are latencies that are added on top of whatever 5G has, right?
Okay, so one last short question.
Yeah, so sorry for the late hour. Anyway, so being a completely applications guy, maybe the only one in the room, I'm not sure. So it's more as in a comment than a question, and it's good to see that the network guys are taking that into consideration, because being an application and a roboticist at Seoul, and in this case, the very particular case that you started by presenting, the offloading, and again, a very controversial statement. I don't believe that much in offloading or in very specific, I'd say critical applications. Although there is some trend of ideas about offloading the control, the actual control of the car, of the vehicle, of the robot, whatever you want. I've heard about that trend. As an application guy, I completely abominate the idea. So what would be but it's good to see that the things are being considered in terms of application level, because as you say, offloading and getting back to the response will take some time. And even the example that you gave about offloading part of the SLAM, the pose adjustment would be based on the past, right? Because in the meantime, in that 1 or 2 seconds,
previous trip data, yes.
Previous trip data,
right. So there is an assumption that the drift is on a short time window. The drift is small, right? Also, the reality is, and you know, we can argue about the details, and I'm not the right person to actually participate in this argument, but I just asked, right? Okay, a car lane has a certain width, right? In the response time that you have for your pose update, the question in many cases is, have you drifted out of your lane? That's, you know, the question is, how much drift is bad and how much drift is acceptable, right? So you need to respond fast enough so you know you're not going to be in another lane, okay? That's really simplifying it, but it's a good first order approximation, right? And if cars actually don't, compared with computers, they move fairly slowly, right? I mean, really, okay? And so especially they go fast this way, but this way and this way is a little bit slower. So I understand your concern about the offloading the control of the car, which I interpret as meaning you press the brake pedal and you're going to send a message to the cloud saying, do you really, really, really want me to brake? That sounds like a really bad idea.
It was not exactly in that, but even in the processing. The camera sends the image, it's being processed in the cloud, and then, okay, then the cloud sends the results. So there's a car here, there's a pedestrian there.
No.
On that level. So.
The brakes need to work purely, entirely on the car. You know, and I understand that, but again, the whole point of being able to use sensors is that you can see that somebody is in the road before maybe the driver can see it. So that gives you a little bit of time to notify the vehicle, right? So I'm not going to say all these problems are solved, but I think there are cases where this is suitable. My bigger concern is that if you have an older car, you don't get this technology, right? So that's really the concern, right? And you know, I don't know the answers, right? I was honestly surprised by what we discovered here, okay? And I'm very familiar with TCP, and I'm very familiar with how IP works and the data link layers work, okay? So, and I was surprised to see how much impact it has on performance. Here's the problem. Most application data that is sent in short flows, which means that where the impact of the latency is the highest. That's the problem. If you send a gigabyte, nobody cares.
Okay, so thank you, Peter. So, to close the session, I ask João Silva to give final words.
Okay. Thank you. So just a very quick final statement, because I know that we are passing a bit the hour. So just to thank everyone that attending our final workshop for FLOYD, to the ones that are in here and also attending remotely. Also to thank everyone that worked for FLOYD project during these 2.5 years. So we were able to present the results and some of the work done today. Also a special thanks to the projects invited, to the advisory board, to the keynote speakers as well for their presence today. And also to close this, to have a nice afternoon and to thank you very much for attending today.
Não há coffee break agora, mas podem ficar o tempo que quiserem a confraternizar.
Agora vou me embora.
Mas-te embora.